thank you all for coming here. This is indeed quite an impressive audience for a workshop. I'm really hoping that we will be able to kind of satisfy your yearning for learning about safety critical control over the next 4.5 hours. So thank you once again for giving us the honor, for giving us your time to listen to us and to listen to our wonderful speakers. So just to say what they say when you get on board on some airplanes, this is a workshop about learning and control for safety critical systems. If you don't want to be here, please leave now. After this, we're locking the door and you're staying here for the next 4 hours. This should work. This does not work. Next slide. There we go. Okay, so before we get to the most interesting part, which is the speakers, I just kind of want to briefly introduce the three of us who are organizing this session and kind of provide a high-level idea of what we are going to be talking about. So the three of us are Negar Meir in the front row here. Negar is an assistant professor at the University of Illinois Urbana-Champaign, and her work is on safe control and human-machine interactions for teams of autonomous systems. My name is Melkior. I'm also an assistant professor from the University of Illinois, and I'm interested in resilience and guaranteed performance for systems in complicated, uncertain, changing environments. And our third organizer, who unfortunately couldn't be here today, is Yas Savash from, he just graduated recently from the University of Texas at Austin with his PhD. He's now a software engineer at Neuro. And his research is on verifiable safety and security for autonomous systems that operate in shared environments. And so kind of the big story of today's workshop is the union of all of these buzzwords that the three of us mentioned here in our research interests. And really it's guided by this idea of what will future machines, future vehicles, future systems need. And those needs go from individual ones, where in a world where autonomous controllers operate all of the world's vehicles or operate in some sort of a shared fashion with humans, all of the world's vehicles from unmanned from unmanned aircraft vehicles to cars to kind of experimental vehicles that also interact with humans on a regular basis, to wider needs, which is infrastructure that will also be to a significant extent autonomously driven, from power grid, transportation grid, public transit. Again, this big notion of urban air mobility. All of these things and beyond, all of humanity's exploration missions, underwater, in the air, in space, in all of these things, safety is critical. Whether it is because we prefer not to kill humans, whether it is because we prefer not to wreck machines because they are expensive, whether it is because the missions themselves will fail if something bad happens. And these features show up throughout domains, from autonomous vehicles to infrastructure to kind of exploration. But kind of, so this perhaps tries to answer, what are we talking about? Why are we talking about this? Let me perhaps try to answer, why are we talking about this now? Why is this the right time to have a workshop on safety critical systems? Why is the time ripe for safety criticality now? And I composed a little idea of how I imagine control evolved. And of course, this is very subjective, but I kind of see 4 phases, and this is the way we kind of teach undergrads in schools, and this is the kind of time-varying evolution of control, I guess. At the beginning, we were talking about what broadly, let's call it process control. Control of these systems that we have some model for. We're generally interested in simple control tasks, some sort of asymptotic convergence, minimal overshoot, long-term behavior, transient behavior, things like that. And the control laws that we were thinking of at the time were empirically driven. There was a lot of tuning. It's this whole story of PID, of Bode plots, of Nyquist plots, all of these things that are kind of classical control. And this is not to say that they are irrelevant, certainly not, but they're kind of the classical start of control. And then from there, we went on to something a bit more, with a bit more guarantees, and that's this idea of geometric or geometry-driven control. And there we started being interested in more complex specifications. We started being interested in state reachability, controllability, reach avoid, which is kind of the beginning of safety critical control. And we started doing these things with analytical methods. So methods that are hopefully no longer tuning and simulation based and seeing how things work. And so we developed these criteria for whether a system is controllable, whether a system is stabilizable, how quickly it converges, the Lyapunov theory, all of these things. Then we realized that, okay, these specifications are a bit more complex than the original ones, but they're still not exactly representative of what we want autonomous systems to do in real world. And what we want to do is we want to control multiple agents at the same time. We want to control them in environments that might be adversarial, that might be changing over time. We want to have these big, complicated missions that might be based by an automaton of some sort that says, first go there, then go here, or go there, then do this. So these big, rich frameworks of missions. To do that, we started playing with learning. We developed this notion of learning-based control. The problem is that in its kind of origins, learning is, again, back to empirical thinking. It is best attempt kind of black box thinking of, I will do something and hopefully it will work properly and I will test it a million times and a million times it will work properly, but I still don't have guarantees. And that brings us to today's workshop, where we want to keep these very complicated specifications that we're talking about, while on the other hand, we want to start getting guarantees for the control systems or for the control laws that we are developing. We want something that is analytical, that we can mathematically treat with rigor, yet agile. We want something that is broad-reaching, that works across domains, yet it is precise. And in some sense, this is a, whether you want to call it a struggle or a kind of confluence of two things: learning, or the need for learning, and the need for guarantees. So learning, on one hand, provides an exciting opportunity to adapt to unknown environments with significantly less structure than would be needed by classical methods of robust and adaptive control that are more conservative kind of by design. And the world needs this. The world needs agility. The world needs adaptability. It needs autonomy. So it needs learning. On the other hand, by the very nature of learning, which is extrapolation from observed events, from observed models into unobserved, obtaining the performance and behavior guarantees for learning-driven systems is challenging. And the world rightly demands that we provide some proof of lack of danger to the surroundings, explainability for what our control systems are doing, some discussion of constraints, whether it is budget, whether it is performance, that we can fit our control laws into some sort of a regulatory framework. That brings us to safety requirements. We need autonomous systems to provably safely interact with not just their teammates, not just all autonomous systems, but autonomous systems and humans. We also need the system that is still learning to remain safe while it is learning, to remain safe to itself and others. We need a system that is aware of its uncertainty and remains safe no matter what the ground truth that it might not have learned yet is. We also want, after adverse events, the system to recognize that there has been an emergency, to adapt not just its plan, its control law, not just make minor changes, but if needed, to adapt its entire mission. And to do that, we need to start thinking of safety not as a property to be verified at runtime, but as a design constraint of the first class, in a sense, as something that we explicitly put forth as a part of the requirements for control design. Now that's hard. And I just listed some of the thousands of challenges that one could pick out here. How to recognize, understand, and respond to others' behavior. How to, once that is done, how to promote joint safety by communicating with others. How to share needed information in this communication while preserving one's privacy. How to formally describe what we don't know, this story of unknown unknowns. How to produce plans that are robust to any possible ground truth. How to recognize off-nominal conditions and how to respond to them without prior experience. And finally, how to determine one's own capabilities in real time after a catastrophic failure. I don't claim that these are all the problems, and certainly our speakers will mention many more of these, but these are substantial challenges, each of which can be technically written down in terms of a mathematical problem under technical assumptions that we can aim to model and solve. And to do that, we cannot just rely on methods of classical control or even methods of kind of geometric control. We need to convene experts from multiple areas to kind of bring their expertise in understanding all of these features and understanding observed behavior. We need pattern recognition. We need specification inference. In figuring out appropriate responses to unknown actors, this is almost by definition a game theory or a mechanism design problem. In talking about communications, which are certainly needed for safety for multi-agent systems, we need information theory. In order to speak about complex specifications and determine capability of systems, of unknown systems, we need to talk about model checking, about formal verification, about reachability. To talk about risk to safety, we need to talk about optimization. And this was kind of our running idea of trying to build this workshop, trying to bring as many experts in as many of these fields as possible to tell us what they're working on, tell us their side of the story and how it fits into this big high-level framework of safety critical control. And so now I want to give the floor to Negar, who's going to introduce our speakers.
Right, thanks, Melkior. So now comes the exciting part that we want to hear from our speakers. And I'm just going to briefly introduce the speakers that we have so that we have enough time to hear from them and learn about their thoughts. So we've tried to have experts from both industry and academia to hopefully have a good sort of understanding of different perspectives that are out there and learn about the challenges that each one of them is facing and the ways they're thinking about the problems. So first, we are going to hear from Eric Wolff, who is a principal research scientist at Motional. And Eric is going to talk about machine learning-based planning for self-driving cars, which I think has been one of the major applications and motivations for many of the controls people to think about challenges of safety and autonomy in particular. And we're going to hear his thoughts on what are the challenges and opportunities that exist for using machine learning-based methods in planning and decision-making when it comes to control of self-driving cars. Then we will have Professor Necmiye Ozay. She cannot actually make it, but we are excited to have Necmiye as a student who will be presenting on safe reachability for unknown systems with bilinear optimization. So Kwesi will actually talk about how we can even think about controlling an unknown dynamical system to safely reach a target set. And I think this is relevant to what Melkior was mentioning regarding specifying the properties such as reachability when you are uncertain about your system. So we have actually a theme of how to deal with unknowns when it comes to control of the systems. Then we will hear from Karen Leung. She is a research scientist at NVIDIA. She will soon start as an assistant professor at the University of Washington. And it's actually interesting because she's going to talk about how to expect the unexpected through a Hamilton-Jacobi reachability framework, which is actually something that has been developed in classical controls, I would say. But now she's going to provide some insight on how we can leverage these tools to provide more guarantees for more of these modern control techniques. And she's going to talk about how we can certify the performance and safety of learning-enabled robots when they are deployed in safety-critical settings using the framework of Hamilton-Jacobi reachability. And we've actually tried to have these speakers such that they cover different aspects of the challenges that Melkior mentioned. Next, we will have Lillian Ratliff, who's an assistant professor at the University of Washington. And she's actually going to talk about another aspect of having learning-enabled systems out in the world, which is closing the loop in learning-enabled systems. What happens when we are learning from the data that is dependent on the decisions that agents make? So she is going to focus on the interaction between technology and algorithms in the design of learning-enabled systems. So it would be a very different aspect of like the data that the autonomous system is going to learn from is going to actually depend on the decisions that they take and the humans make. So how should we think about this dependence and how should we even account for that dependence in our decision-making loop? Then we are going to have Kevin McDonough from, he's a senior research engineer at Burrell Applied Research. And that would be the talk which focuses on information. Melkior was talking about the role of information and how we should think about information and communication and possibly ideas in information theory. And that doesn't mean that Kevin is going to cover all of those, but we would love to hear Kevin's thoughts on information for safe and efficient decision-making in urban airspaces, which is another emerging application area where the issue and the challenges of safe autonomy are very relevant and very important if you really want to make that the next generation of our transportation systems. So Kevin is going to talk about decision-making in urban air mobility through the use of non-conventional information sources for risk reduction. So we will have some perspective and thoughts on the role of information and how to think about for these new generation of autonomous systems. And finally, we're going to have Changliu Liu. Changliu is an assistant professor at CMU. And she's going to talk about safe control and continual learning for collaborative robots. She will tell us about her work and her thoughts on safety of autonomous robotic systems when they are used in uncertain and human-involved environments. Like Melkior said, one of the challenges is that once these systems are interacting with humans, they're sharing the environment with the human. How can we say something and certify the performance of these systems when they're around humans? And in particular, the issue of continual learning. If they're just learning from their repeated interactions, what does safety even mean in that context, and how can we formalize safety in that context? So we would love to get us started to hear from our speakers, and feel free to ask questions once the speakers are done. We hope that this is an interactive discussion where we could share thoughts and learn about each other's perspective towards this problem. And hopefully by the end of the workshop, we will all be convinced that there are some interesting problems that we all want to work on. So let's get us started by having Eric.
maybe while Eric is getting set up, just in terms of scheduling, we'll proceed with, so there's 6 talks, and we'll do it in 3 groups of 2. So first, Eric and Kwesi will talk from, so 1:30. We'll have half an hour coffee break. After that, we will hear from Karen and Lillian from, I guess, 3 to 4. We'll then have another 15-minute break, and then from 4:15 to 5:15 roughly, we will be hearing from Kevin and from Cheng. You have to share your screen on. So.
Recording in progress.
Good.
Are you unmuted?
I'm unmuted.
Oh,
One should be muted, one should be.
Okay, everything should be set now. I think this was the first AV challenge of the day. And so we'll get into the other AV challenge, autonomous driving. So thanks so much for having me. Eric Wolff, Motional, and I'm going to be talking about some work that we've been doing on machine learning based planning for self-driving cars. So Motional, we're a self-driving company with kind of background going back to the DARPA Urban Challenge. So kind of MIT and CMU heritage through Autonomy and Automatica. Currently, we do a lot of our testing in Las Vegas, and we've been partnering with Lyft and now Via there. So we've given a bunch of rides to the public. If you're ever in the Vegas airport, you can open the Lyft app and there are opportunities for that. I think you get randomly selected. And we're also doing a partnership with Uber Eats in LA. So we have a fair amount of cars kind of on the road, operating in some interesting environments. And so, for Motional research, so I lead a research team for autonomy there. And we're focused on using ML to model the hard parts. So a few years ago, this would be perception and maybe prediction. And we've kind of kept going to go down all the way to planning. We haven't included like tracking control yet, but maybe if I give a talk in another few months, maybe that will also be there. And also, we want to support ML research for autonomous driving. And through that, we've been releasing data sets. So new scenes, which has had a very large reception. That's like 1,000 scenes in Singapore and Boston for object detection, motion prediction, semantic segmentation for LiDAR. And recently the new plan, which is a 1,500-hour data set across multiple cities that is for those tasks and also much more focused on planning. So we have a teaser for that out, and the full data set should be out later in this summer. So additionally, we've been publishing some papers and in both of these areas trying to support the ML research community. And so today I'm going to talk mainly on ML planning. And we've kind of over the years have come to realize that programming a self-driving car is very hard. Out of grad school, I was like, we'll do this and it won't even take that long. And in 2016, we'll be there. And I think a few folks thought, we're pretty optimistic about that. And, when you get into the nitty gritty, there's so many challenges for sensing, right, we see with cameras and LiDARs, so the inputs are very high dimensional, pixels, point clouds, there are occlusions, kind of that give fundamental uncertainty, lots of different types of objects. This is a pedestrian, probably looks different from a point cloud since they're carrying luggage. So there's a lot of variation. On the planning side, the behavior really depends on the scene context. So everything around you, all the other road users, the road geometry, your goals, any semantic information like crosswalks, bus areas, you need to observe the past for a little bit and make a quick decision with partial information. And anticipation here is important for like reasonable planning, so that you can drive in a kind of a less myopic way, so you can kind of anticipate and make saner driving decisions. And rules of the road, either they're not complete or just completely not followed. So I used to live in Boston. Nobody has read the rules of the road, so you need to be able to account for that. And so, because of a lot of these challenges, so ML is becoming a more and more important part of driving. So, kind of a standard use case, when would you use an ML solution? And it's if you have a lot of data. So we and many other companies drive around a lot and collect a lot of data that we can use to train our models. A pretty stable data distribution. So stuff isn't changing that much week to week. You have seasonal variation, but it's easy to account for. And for many of these things, there's no good analytical model, especially for perception. For planning, we have much better models. I'll kind of get into that more, but there's still a lot that's very hard to specify, especially when you get into the, what is good behavior, what is not, if you wanted to actually write that down. It's challenging to get a good model for that. And so, right now, I'd say kind of the state is machine learning is very heavily used in perception. So in the upper right is a diagram of a paper we did a few years ago now on object detection, but very heavily used in perception. For motion prediction, what the other agents around us, what the other road users are going to do, it's becoming more and more prevalent. So back in the day, you'd write some maybe expert system, some heuristic model for what pedestrians or cars are going to do. A lot of that is transitioning to be more and more data driven. And this was kind of a paper we had a few years ago as well on motion prediction with deep learning. Planning is partially, so that's something that my team, as kind of a research team, is looking at exploring more and more and seeing how far can we push that. And so to kind of go over, just to give a view of what we're talking, or what I'm talking about here for kind of an ML planner. So for this, we want to learn a driving policy based on expert demonstrations. So imagine we have our safety drivers go out, drive a lot around a city, and we record their motions, we record the sensors so we can build up a view of the environment around them. We're going to give inputs as tracks. So these are like tracked objects. So like we assume we have a working perception system. So bounding boxes, velocities, object types. We assume we have some high definition map, which is also common in our case for like a self-driving robotaxi. And then we have some route or mission goal information, kind of like a Google Maps, where should you be going? And so for this, we're going to output a trajectory, basically saying, here's where we want to be in the future. And at every 100 milliseconds or so, roughly, we will execute this again, come up with a new plan, and then we have a tracking controller on the car that will follow this plan. And the model here, is some deep neural network with some mix of learned and hand-engineered features. And I'll go into details on something we've been doing recently with that. So now we've kind of given a view of what I mean by an ML planner, and this different people use different definitions. So kind of question is, why build this? So I personally come from a motion planning and optimization background, and there are a lot of great algorithms that have amazing convergence properties and are very generalizable and to a great degree. And it seems like you're kind of throwing out a lot by taking a step away from that. And so, one reason is adaptability. So one of the earlier companies that formed Into Motional, we were doing a lot of driving in both Boston and Singapore, and like a hand engineered planning stack that works in both is tricky. And then it's like you have certain behaviors that really are apparent in one area. So for Singapore, you have a lot of double parked cars. In Boston, you have a lot of very erratic jaywalkers and bicyclists. There's like a lot of different variations. The driving behavior is very different as well. And so kind of a learning-based approach gives the benefit of you have a straightforward procedure to go into a new city, a new region, in terms of you are collecting the data, you train your model on the new data, a model for that region, and then you deploy that. And so you can kind of focus on learning the nuanced driving behaviors in each area. The second is automation. So, if you have a classically developed planning stack and you go out and you drive and you have errors, you have takeovers, the safety driver had to take over due to poor behavior, you need to basically have a developer sit down, think over how to fix the issue, potentially rewrite a lot of code. It's rarely just a small parameter adjustment. And it's just a slow process. And these things start compounding over time. And if you imagine also covering a bunch of different areas, making sure that the system works as expected everywhere you're deploying starts becoming a huge task. So, there's a ability to automate some of this by when you get failures, adding those into the database and retraining in an appropriate manner. And then the final kind of area is affordability. If you are already doing machine learning for perception and motion prediction, like many companies are, you're not really adding much in terms of infrastructure. A lot of the kind of shared infrastructure is there. So it's not like a tremendous new investment for this. And so I must say I came to planning from a very classical approach, tried a lot of things, and all of these things, or the top two, came up a lot from personal experience. And so there's kind of some common approaches you could use for building an ML planner. So the first is imitation learning. And so this is, you create your data set, you have your safety driver, go out, drive, like a good driver, and you try to mimic exactly what they did. You try to represent the scene so you can mimic the exact actions they took. So you're kind of parroting back what they did. This can be quite fragile. The second is inverse reinforcement learning. And so in this one, you're kind of a detective saying, we know the safety driver, they're an expert, they're optimizing some cost function. If only we could learn what that cost function is, we can use that to score new behavior. And the third is reinforcement learning, where assume you have a cost function, reward function saying what is good behavior. And you have an environment model that's pretty high quality. You act in the environment, you collect your reward over time, and you try to figure out, what actions did I do that led to a good reward. So, I think there's a lot of promise in all of these areas. They each have, different challenges. For RL, the big challenge is the reward correct? It can be very tricky because you don't quite get it from rules of the road. We're going to focus on IRL for this one. And we found that this was a nice fit in terms of kind of learning what an expert driver was doing. And so we just recently submitted a preprint for this driving in real life with inverse reinforcement learning. And so this will be up on archive, I think either later today or tomorrow. So this is very new. It's like through the submission process, waiting in queue. And so to our knowledge, this is the first inverse reinforcement learning based planner to drive in an urban environment. So we took it out in Las Vegas where we do a lot of testing, and we'll go into more details here, but just to kind of give a flavor of the environment a little bit, this is just driving down on the Vegas Strip. And so this is during the day, like moderately dense traffic. Basically, the Strip, it's kind of up and down, and then you have some pickup drop-off areas near the hotels. And so We'll go into more details kind of throughout, but I just wanted to give folks a little bit of flavor of what the environment looks like. You see our cars in the middle, and then the other tracks are represented by these translucent bounding boxes. And this is also fairly similar if you think about the info the planner has, the other tracks, the map info. And so the overall architecture, we generate trajectories, we run these through a safety filter, and then we do a learned scoring module. And so basically the first two are hand engineered, and maybe these are more like ACC type tasks to do. And then we can focus the learning on the scoring part, which worked quite well for what we were doing. Some benefits are, we have relatively interpretable features. For the safety module, it's pretty lightweight. It's very few lines of C++ code. So you can start thinking about more in terms of interpretability, larger guarantees for that. So, the overall architecture for the model. So we have the scene context here. It's not, we don't feed it to the model as an image, but this is just an overhead image kind of saying, showing some of our ego in red parked at a traffic light with a pedestrian crosswalk in front. The other cars are these yellow boxes. The orange squares are pedestrians. So anyhow, the scene context is our information, the map, the route, other road users. We use that to do first trajectory generation, where we generate a large number of trajectories. Then we run these through a safety filter, which does a small amount of kind of sanity checking, making sure that the obvious unsafe behaviors are eliminated. And then on the remaining safe trajectories, we do a learned scoring module there. And then we select the one that scores the best, and we feed that to the tracking controller. The tracking controller tracks it for the next 100 milliseconds or so, and then we repeat this loop. So now kind of jumping into each of the separate components. So for the trajectory generation, so we have a simple model here for kind of hand engineering these trajectories. Basically, we want to enforce, we follow the route. We have dynamic feasibility, that any additional assumptions or constraints that the drive-by-wire and tracking controller layers have, and like continuity, minimum acceleration from a stop, all of these things, that those are handled appropriately. So we have a clean interface with the car. And also that we have a pretty wide range of behaviors to score over. And so these are just a few examples. So the white is basically the density of trajectories here. We have a lot of overlap due to different acceleration profiles. So basically along the route, there's a pretty widely spaced set of different acceleration profiles, taking into account different driving behavior you might want to do. Then the second aspect we have, which is engineered, is this lightweight safety filter. And so basically, this helps us very cleanly make sure that we are enforcing things related to no collision with any of the trajectories with the environment, that the time to collision is above some threshold, so that's a little bit broader check. Also, like a time gap to the car in front is sufficient. And effectively, the overall approach here is kind of guaranteeing kind of recursive feasibility, saying if I follow, show me a trajectory, if I follow this for the next, say, 1 second, then is there a continuation of that trajectory that would be safe? And so basically here in the image, it kind of demonstrates that where the ego is in red, the yellow is like, say, a stationary car in front. You can see we have 3 trajectories that would collide, or sorry, 3 trajectories, 2 that would collide. We assume for each one, we follow it for, say, 1 second. Then we have a braking trajectory that exists that we know we could switch to after a second. This could also be an acceleration trajectory depending on the exact setup. And then after that, we say, okay, the first two are fine because the first one is safe completely. The second one is not safe, but we know we can modify it later on to be safe. And so this gives us kind of a minimal wrapper where we don't want to intrude too much. I think in some like the hybrid systems, model checking literature is like a minimally permissive parent type of stuff where you want to put some bounds on behavior so you don't get outside of the safe set, but you don't want to be too constraining. And so this for us basically covers long tail events, increases reliability. It's something we can show to people across the company and be like, hey, these are at the end of the day, anything coming out of the model is going to satisfy these responsibilities. Then, so the first two main components have been hand engineered. The learned component is the trajectory scoring. So for this one, we looked at we wanted to go with a pretty lightweight model. So this was kind of the first thing we took out on the road. We wanted to see what, could we go with a lighter set instead of maybe like a full on like transformer-based model? Can we just bring in some kind of motion planning intuition and then kind of learn the exact parameters for kind of how to mix everything together? And so we broadly have some features related to safety and comfort. At each time we take in the scene, we generate trajectories. Along each trajectory, we extract features. So one trajectory, for different like the maximum jerk or acceleration or how we're doing compared to the speed limit. Then we run this through a neural network model with self-attention. And we did a few experiments with different architectures, and in the paper there are more details, but this worked pretty well where we kind of siloed these features a bit and then mixed them with the masked attention layer. And so overall, this is actually a pretty light model. So this is maybe like 180,000 parameters. We think of a lot of deep learning models, right? That'd be very small. From a control standpoint, that's like people are like fainting in the back, and and so for the data, so we used a kind of selection from new plan. So this is going to be released this summer. It's about 500 hours of driving around Las Vegas. And so this data will be part of new plan in a couple of months. So we're excited for that. On the right, there's some views of kind of what different scenes look like. The loss, like I mentioned, we're using an IRL formulation. Basically, the trajectory closest to the expert should get the highest score out of all the trajectories. We generate a bunch of trajectories, and the one closer, we train it so that it will give the highest score to the trajectory closest to what the expert actually did. For evaluation, we did closed loop simulation. And so this means that we take a step along our plan, and then we keep replanning. And for this, the evaluation about like a 10-second scenario. And this is important because as you're planning, you're feeding back your previous model outputs into your input, right? So if you're making mistakes over time, pretty soon your input is looking potentially very different from your anything in your training set because your expert isn't making these same mistakes. So that evaluation, doing that in closed loop is important. We did a fair amount of data augmentation to kind of help with the distribution shift. More details on that in the paper. And also having this constructed trajectory generator helped kind of focus us back towards the lane. So that was something else that reduced the sensitivity to distributional shifts. And we did the evaluation on 1,000 scenes. So here are just a few qualitative examples. So we have ego starting from stop. So at this point, the traffic light is changing. Red is the ego, blue is the expert. So you see we're a little bit slow off the start here, but fairly consistent planning. Additionally, stopping for a lead vehicle. This is basically following behind. We're a little bit speed limited by the car in front of us. And this is a light cut in where this car is kind of merging in front of us off here. And so in terms of, for more quantitative performance, we looked broadly at like safety, comfort, and progress as being kind of high level things that you would care about. And here, this is just comparing against a couple of kind of simpler expert models. So this is like a constant speed lane follow. This is kind of like the lowest baseline. That's like the simplest thing. So that just gives a sense for the metrics, right? That's the stupid baseline. So your metrics should be doing well. This one is very comfortable though, right? You continue going the same speed. Intelligent driver model is basically like an adaptive cruise control model. In the literature, we tuned some parameters to get kind of best performance here. Kind of ours especially with the safety filter, so we did it with and without the safety filter, ends up being fairly performant, especially in terms of like collision or tailgate rates, which we found to be really, really important. So that collision rate was really the key thing here. And so for this, we took it out in fabulous Las Vegas. We have a big operation there. We do a lot of testing. So we put this through our some simulation tests, closed course driving tests, made sure it was good to go, and took this out with a safety drive and operator, like standard procedure. So basically, this is kind of with the safety filter, we prevented basically a couple takeovers on this loop. We drove it for 8 and 6 miles, just to give a sense of not a huge amount of driving for the prototype, but just enough to show that we had some kind of consistent performance here. And I'll just run both of these. These are kind of the two different types of driving you see in Vegas. A lot of it's on the strip where you're accelerating from a traffic light and then coming to a new traffic light further down. And the other is these kind of pickup drop-off areas where it's slower speed, going around like some tighter control around these roundabouts. And so, for this workshop, it's like, how do you actually assure safety of something like this? I think a lot to be said for a simple kind of safety filter type approach. There's really no silver bullet though. I think that also comes in with like just the overall safety checks for like an ML system where, the compute part is pretty easy. It's like you're gonna put this on the GPU and have some guarantees in terms of how long it's going to take to run. For the data pipeline, are your input data correct? Is your evaluation correct? Is the training pipeline correct? You can do more, classical approaches for the good software engineering to check that. For the model, we basically did the top 2 here, looking along a large test set that we met performance, and also, have some non-machine learning safety checks. These are, a couple other areas if you had some more introspection in terms of if you're within your operating domain or uncertainty estimation. But I'm not sure if there is a silver bullet or if it's just careful construction of a number of good techniques. And so, yeah, I just want to conclude with, whether it's good or not, ML is really advancing self-driving cars kind of throughout the stack, from perception through prediction, and increasingly in planning. And excited that we're able to release some work on using an IRL planner to drive in Vegas. And so that paper should be up on archive either later today or tomorrow. And so with that, I want to say thank you so much. I'll take any questions that you guys have.
Thank you, Eric. I think there were some questions on Zoom. Are there any questions? Oh, please.
Yeah. Yeah, I was just curious. It was great talk, by the way. I was curious about the safety filter. You have it after the trajectory generation process and before the control. I'm just wondering, are there any other, where like the safety come in other places in your set, or in particular the planning control set?
Yeah, so at the drive-by-wire level, there are limitations that will prevent, crazy torques or whatever applied to the vehicle. And in the case that would make it, like uncontrollable. So there are lower level safety checks. Of course, for this, the safety filter here, this was kind of like a pretty hard filter, right? It's like this trajectory is good or not. You could imagine putting this after the ranking or trajectory generation, and you could imagine having that be something where it projects it to some safe set or something like that, or like moderates it. So you could imagine doing a lot more with a safety filter.
I have a question. So which is safer now? A car driven by a human or a self-driving car? Are you at the point? And one of the rationale to me for self-driving cars is to make them safer than human drivers.
Yeah, so I think it depends on the software, right? I think it depends on the company, on the software, on the operating domain. So companies now so we've done some limited driverless testing in Vegas, and not on the strip, but with no safety driver, no safety operator. And I know Waymo and Cruise are doing more and more driving, without a safety driver in parts of Arizona and San Francisco. So, I think companies are coming a long way. An attentive driver, though, is a very high bar, right? If somebody's actually paying attention, that's a very high bar. Sadly, most drivers aren't attentive. They're like on the phone or thinking of other stuff. Or
they're attentive for 99% of the time. One moment you lose attention.
Yeah, that's the danger. So, but
Do you have a number of safety critical scenarios that you run through a standard set accepted by industry for testing these algorithms?
I think not at like an industry level. I know we have internally a pretty large suite of simulation tests that test the entire stack, and also for closed course testing to verify a new build before you take it on public roads.
And and what about government standards? How's that coming? Will there be a set for highway safety?
I don't know all the details on that. I know there's been a lot of there've been like discussions with AV companies and different local governments and more broadly. I don't know specific details. I would assume eventually there will be, but I don't know any details.
So a lot of this optimization seems to be predicated on the fact that the safety driver, we know what a good driver looks like. And this is true for mostly non-autonomous traffic. But as you start tipping over into more autonomous traffic and maybe even saturated with autonomous traffic, how do you think some of these optimizations are going to change? And how are you going to assess what is best for that?
Yeah, no, that's a good point. I mean, it's unclear. So if you had, say, a future driving system where all the cars were autonomous, or most of them were, and maybe you're going much faster, much closer, maybe safety, you can have good safety, but the cars can maybe drive closer together or something, less following. I don't know if they're communicating. So I don't know. Probably won't look like this. I don't know exactly what expert you would need to find for that. Maybe at that point would understand, what good driving behavior is well enough so that RL approaches would be very favorable in that domain. I don't know that.
So you have two questions in the chat. I'm going to read over the question. So Venkat Raman is asking, he has a question with respect to the trajectory scoring part that you mentioned. He's asking, how are you propagating system and perception uncertainties? Suppose if car A is trained with 1 million data set and car B with 2 million data set, how should I choose the best car? The quality of the train data matters a lot.
Yeah, and so effectively for like the best training, so here we trained this on data that was auto-labeled. So we basically ran an offline perception system to provide labels instead of manual annotations for the other tracks. And so that'll be part of the new plan data set. For that, using those as the inputs, we don't really have a high level of uncertainty in those. When you think about running this online though, you do have uncertainty from the tracker for each object, and you can include that as well into the feature space to give some sense of the uncertainty there.
I just unmuted myself. And next, Apurva asked the question of, can you please provide an example of a scenario in the long tail case that your safety filter was successful in catching those?
Yeah, so I would say this isn't like super long tail, but this is maybe long tail for prototyping and like, initial work here. So we had some pretty aggressive cut-ins, like dangerous kind of cut-ins that the safety filter works with that we had not seen before in the training data. We knew cut-ins are a big important thing, but not to that degree.
Something. No, I think that's just my screen. Yep. Yep.
Oh, thank you. Also share this one. Okay. That works. Perfect. All right.
Kwesi Rutledge.
Thank you again for the introduction. Yes. Thank you very much for giving me this opportunity to speak at this workshop. Necmiye really would have liked to attend, but she had some last minute business come up. But yes, today I will be talking about safe reachability for unknown systems with bilinear optimization. This is based on some recent work from our group at the University of Michigan, Ann Arbor. So that's my particular area, but I would not be a good lab mate if I didn't advertise for the other areas of our group that are also touching on learning and control as well. The first one, some of you might have seen, is on offline learning and control for, yeah, sorry. Small, awesome, thank you so much. For offline learning for control with safety and reachability guarantees. This work is being done by Glenn Cho in our group. That our group at the conference. I've linked 2 of his presentations. Yes, he's very productive.
I think we are not able to hear the Zoom. I'm actually speaking for the Zoom audience.
Oh my goodness. Okay.
Okay.
Too many technical difficulties. Yes, so you must also move the boxes safely to this new apartment. And you also have a deadline with which you need to complete this move. So I can't wait all day for my friend to move one box, for example. Okay, I argue that these characteristics exist not only in the box mover problem, but also across a wide range of important control theory problems. And I'll look into how problems with these characteristics have been addressed in the past using this idea of the exploration exploitation trade-off that might be familiar from learning circles. So, the way that we think of, or the way that I've thought of exploration and exploitation in the context of control is in trading off parameter learning versus robust control concepts. The area of adaptive control offers some direction on how to do this trading off. For example, adaptive controllers based on barrier functions are able to achieve zero tracking error when some robust controllers cannot, as shown in the figure on the right. In terms of the box mover problem, an adaptive controller would somehow identify a strategy that maybe shakes the box a little bit to determine what's in it, while also making sufficient progress towards your goal and eventually achieving the task. Importantly, the exact mass and moment of inertia of whatever's in the box might not need to be exactly learned by the adaptive controller. Usually it just has to get somewhat close. In fact, it can still achieve the task even if it doesn't know the true parameters. Unfortunately, adaptive controllers are frequently much more complicated to design, and little work has been done to make it easy to incorporate these complicated finite time horizon tasks, like the one that I mentioned before, into their design process. So what we tried to do through this work that I'll talk about today was specifically address these last 2 points. How can we make it easier to design adaptive controllers that satisfy these types of complicated tasks? And so the formal problem statement that we would like to solve to kind of create an ideal version of this problem is we're going to assume that you're controlling a linear system. You're controlling a linear system, but the parameters of this linear system are unknown to you. So in this case, the A, B, and then this set where the disturbances are coming from are not known to you, but you know they're coming from some maybe finite set. You also know the initial condition from which you start the task from. You know the deadline that you're working with, the time horizon T, as well as the target set that you're trying to reach, the task you're trying to achieve. And your goal is just to find a controller such that regardless of which of these modes or these tuples, the A, B, Ws are active, you can guarantee this controller with no intervention from you will guide the system to achieve the task. Importantly, I'll also add the assumptions that our disturbance sets, most of the sets in this problem are polytopes. And again, I'll mention that there are a finite number of these tuples, so there's a finite number of options that this linear system can be in. To make this problem a little bit more concrete, I'll discuss or try to connect most of the theory today to this box mover or this drone mover system. Basically, we're going to have this drone and we are going to control the position and velocity of this drone in the altitude direction only. Again, to simplify things. So the state will be in R2. The control input is a thrust force in the Z or altitude direction, and the noise is a little bit of deviation in this thrust force. And the unknown parameter here is the mass that you're carrying, so the package that you're carrying. We'll assume that you start the problem from a height of 1 meter above the ground with 0 velocity, and your goal is to reach a height that's roughly between 2 and 3 meters in about 8 time steps. With this problem in mind, let's consider our approach as the following. I'll walk through each of these pieces so you don't have to remember all of them. But again, the output of this pipeline is an adaptive controller, which we can guarantee satisfies some safety or reachability constraints. As with most adaptive controllers, one of the most important components is the estimator that's estimating the unknown parameters. So we'll start there first. The estimator that we're considering, or that we did consider here, is the consistency estimator. I just noticed this one. There's a way to minimize this. Okay. That works, but okay. The consistency estimator has this complicated definition, but the idea is visually shown on the right. You have some data, usually in the form of states and previous inputs that you previously executed, and you basically find which modes of the system are consistent with that data. So what modes could have produced the data that I'm seeing now? If you saw the blue data point, then that would be consistent with the blue mode or the blue mass of the drone. If you saw the magenta data point, then that data was only consistent with the magenta mode or the magenta mass. And then if you have this data point that's kind of in between or inside both regions at the same time, your consistency estimator will tell you essentially, I don't know which mass produced this data. You should be robust to all of the masses currently. So, okay. We're going to be discussing sequences of these estimates. So this basically expresses how knowledge about the world changes over time. And we're going to collect these sequences into something called, this is going to be annoying, an exploration exploitation profile. Yes, I'm going to explain more about why we call this an exploration exploitation profile in the future. But yes, this is just expressing how knowledge can change in the system over time. So now that we have the estimator defined, we're going to try to define the adaptive controller's domain in this specific problem. So our adaptive controller can be thought of as this function that takes as input, again, the current estimate about these modes, as well as your data, which is again the X's and U's. And one initial question that we had about this was, is the domain of this controller essentially the set of all possible estimates, the set of all possible trajectories that the system can create? Because we are trying to formulate this into a robust optimization problem. What we realized later was that the domain is actually kind of partitioned in this interesting way based on our estimator. So the M input and the XU data inputs are coupled in this way so that you don't need to define essentially a controller with a very large domain. It only has to work on these specific places. And the reason is because, again, this bold M has to be consistent with the data. And we try to formalize this idea of this partitioning of the space of all trajectories with something called consistency set. You can probably already guess where the name comes from. Simply put, the consistency set for an estimate, bold M, is all trajectories that produce that estimate. For example, in the figure on the right, the set of green trajectories would correspond to perhaps all the trajectories that have this estimator output, green M, which is shown on the slide. Importantly, these estimator, the consistency sets Some of them are empty. And the reason for this is something we get into in the paper. But that just means that we don't need to be, we don't need to construct a very large partition. Essentially, there's only a few consistency sets that will represent all the trajectories that we're interested in. And we collect them into something called this M star, this profile M star. Yes. Now the actual domain of our controller is then defined based on this M star. I'm not going to go into this complicated Cartesian product, but by understanding the exact shape of our domain, the robust optimization problem that we formulate later is a lot tighter and can make a lot nicer guarantees. This also shows that there's a trade-off in identifying the domain of this controller or defining this controller, because this fancy set M star that we've defined here is based on checking for emptiness or non-emptiness of this set C. And the set C is this complicated non-convex thing. So it's often hard to do that in a reasonable amount of time. What we can do and what we show in the paper is that you can approximate an answer to what this M star should be by doing operations on this different set called this R set. R is convex, and so it's often much more computationally feasible to check things on R rather than on this consistency set. Okay, with this in mind, we now have the domain. We're going to try to insert control into this process now. The specific controller structure that we're interested in is a disturbance feedback control law. Importantly, it amounts to a linear combination of the data at each point in time. And if we assume that this specific controller is used, this disturbance feedback controller is used, we can modify our definition of the consistency set in a useful way. Basically, that consistency set, as shown on the right, they may not always steer all the trajectories of the system into a target set, but maybe if you find the right controller or the right restriction of this consistency set, you can make guarantees about steering things into the target. And so our overall control goal is to find these disturbance feedback controllers that bend this inner magenta tube of trajectories into the region that we want them to go into. Yes. And again, similar to the last slide, there's a convex approximation for the C set, which we'll use for computation. And I won't talk much more about it, but more details are in the paper. Okay, so now we've talked about what the goal for our control design problem is, to find these Ks that do this bending. How do we actually include that into an optimization problem, into a robust optimization problem? So the adaptive controller design can be thought of as designing a set of parallel disturbance feedback controllers, which I'll try to make clear, that satisfy two main constraints. One is that, again, the steering is done. So all the trajectories from R are steered into our target. This is basically a polytope containment problem. And this is the source of the bilinearity in the title of this talk. Just to give you a brief intuition of why this is, the normal constraint that you get when you're trying to enforce that to polytope inside a polytope looks something like this. There's a linear constraint when you have the hyperplane representations of the polytopes. But we have this weird parameterized polytope that we've defined in this problem. And specifically, these two terms in the constraint are a product of these weird dual variables and this linear combination of the gain matrices K, which results in bilinearity in the overall optimization problem that we're trying to solve. Yeah, I won't get too much into the nitty-gritty details of that. The second constraint that we want to think about to design this adaptive controller is how to select the right controller in time at the right time. Like I was stating earlier, we kind of have a large collection of these disturbance feedback controllers running in parallel, but we didn't make it clear which one you choose when you see a certain data point. I'm going to say that this is the constraint that you want to enforce in order to make this gain selection process causal. And rather than go through a formal proof, I'm just going to give some intuition, which is that online you might see a sequence of knowledge like this, or a sequence of M's like this. And then you might check your M star and say, okay, there are two different sequences that I know about that match the prefix for this. If you obey this constraint, you can basically guarantee that regardless of which of these bold M sequences you choose, the output of the controller will always be the same. It's the rough sketch of why this enforces a causal controller, but again, for more details, you can look in the paper. So, okay, just to summarize the end part of this pipeline, once you have your M star, you can formulate this big optimization problem. You want to find, again, a set of disturbance controllers such that each of these C sets reaches the target. We also add that some input constraints are satisfied. You can also make these state constraints or safety constraints. And then you add in this causal linear constraint, and then it'll find for you an adaptive controller that safely reaches the target. So in summary, what we presented with this first pipeline is first, a method for finding the domain of these adaptive controllers that use consistency estimators. Unfortunately, it's very difficult to find this M star specifically because it's computationally complex. And then the second half of the pipeline is just a bilinear optimization problem that runs quite fast, usually in less than 100 milliseconds. But yes, once you've done this kind of first computationally difficult part, you can then find an adaptive controller that hopefully that satisfies your task correctly. And we use this in first the drone mover system that I mentioned earlier. I'm not going to go through all of the descriptions of this problem again, but I just wanted to show this video that gives the intuition of, for this drone moving, again, an unknown mass, it's able to, starting from that initial position, basically fall while learning about what its mass properties are, and then it reaches the target. And we have a certificate that both it learns something about its own dynamics, and it also is guaranteed to reach the target. Another example that we have, which is useful for illustrating a concept that will come later, is this weird opposing rotational mode system. The system contains two identical modes, basically, except for these A matrices. Basically, the system will spin either clockwise or counterclockwise by pi/4 radians at each time step. And critically, the system does not exhibit a robust control system, but we can see that by applying 0 input, you get very close to reaching this target set in white. And then our particular pipeline finds a solution for this problem with an M star that contains only 2 values. I'll get into more what that means, but basically our pipeline finds out that it can quickly identify which way the system is rotating, and then it's able to aggressively satisfy the desired spec. Yes, I see okay, perfect. So yes, one thing that I was going to add was that something about the pipeline that I mentioned earlier was that this M star is often large and hard to compute, but often it gives us some interesting outputs. In this case, what I wanted to highlight was that our optimization problem has this large M star, but often it only finds like a set of 2 or 3 disturbance feedback controllers that it really needs to solve the problem. And what we discovered was that the constraints that we gave basically give the optimization a lot of flexibility in how it finds adaptive controllers, and it'll usually look for kind of a minimal set of disturbance feedback controllers that can solve this problem, which is an added benefit of using this approach if you're willing to go through the trouble of finding this M star set, which again is very computationally complex. So yes, there's a trade-off then between, again, finding this M star and computation time. So in order to alleviate this trade-off, what we thought about was basically removing this first part of the pipeline, which is really the biggest burden here. The first part of this pipeline is mainly meant to detect when certain consistency sets are empty or not empty. And if you remember from some of your geometry courses, you can actually incorporate this into an optimization problem using something called the Farkas lemma. So you can replace this earlier part by adding in some extra constraints, but it requires you to have some guess about what you think the profile M is. So you need to make some guess, and then the optimization will check for you if that guess is actually correct or not. Again, the reason why you would do this is because oftentimes it can reduce the number of constraints, or it can reduce some of your computation time, even though it might change the number of constraints in your problem later on. So, okay, I mentioned earlier that I was going to briefly discuss why these M's are named exploration exploitation profiles, and this is that part. For this pipeline, I'm just going to give 2 quick examples to illustrate what M means. An M, for example, like this, is basically telling your optimization problem you want to find controllers that learn something about the system at a certain timeline or at a certain deadline. So in this case, by time step 2, I want you to determine what the true mode of the system is, and then I want you to still satisfy the task. But you can also create M's like this, which have kind of like the opposite intent, which is maybe you want to hide the mode information of the dynamics, the true mode of the dynamics from any observer for all time. And if you, again, give this to the optimization, okay, it will similarly try to find a controller that correctly satisfies this, what we would call epistemic or learning-based constraint. And yes, this is just a brief slide showing what this looks like for one of the problems discussed before. This is the opposing rotation example. Basically, we discussed earlier how you can solve this problem using the first pipeline, using M star. And again, because of the computationally complex nature of pipeline 1, it takes a lot of time to set up the problem, even though it's very quick to solve. If you approach this using pipeline 2 or approach this using some M that you like, in this case, this M that discovers the true mode of the system at time 2 or time 1, then your constraint setup time is much faster, but you see the optimization solve time is a little bit longer. And this should intuitively make sense. In pipeline 2, we added these Farkas lemma constraints, which made the optimization slightly harder to solve. So yes, just giving a quick intuition. I see that I'm a little bit over time already, but the future work based on this is that we now have a way of encoding basically knowledge-based specifications, which we want to use to, again, design correct controllers that can adapt or learn to the environment. So typically you have controller or tasks like this eventually do task 1, but we want to move to having tasks that look more like this. So eventually, if you know that maybe mass A is on the drone, then maybe you approach task 1. But maybe if you know mass B is actually on the drone, different task. So as you learn more about the environment, try to achieve a different task. And this is appropriate for many of the tasks that we think about at the Robotics Institute at the University of Michigan. For example, in robotic manipulation, where you don't know all of the parameters of the objects that you're manipulating, or sometimes in motion planning, where similarly environmental factors can affect what plans are feasible over time. Yeah, and also go through this very quickly, but some of our future work also includes safe reachability for unknown hybrid systems. Many of the robotic systems that I mentioned on the last slide are nonlinear or hybrid due to things like friction. These are harder to apply our methods to because oftentimes their reachable sets aren't convex, and a number of other reasons issued on the slide. But the approach to doing many of these manipulation tasks usually is through something like a hybrid linear MPC, which gives us some hope about how useful these methods can be. Yes, and so in summary, apologies, we have this framework for identifying adaptive controllers for unknown linear systems to satisfy reachability tasks. And we talked about you can modify this framework to encode knowledge-based specifications or knowledge-based constraints into their design. We applied this approach to several examples, including this drone altitude control example. And then our future work was extensions to nonlinear systems, hybrid systems, as well as forming these new, or considering these new forms of tasks that involve knowledge. So things that could be expressed with things like with logics like KLTL. Thank you. That's it.
Given that we are a bit over time, I don't know if there's any quick questions for Mr. Kwesi, or we should face this all.
Hi, is it possible I can ask questions from Zoom?
So Venkatram, do you have a question?
Yes, I have a question. Yes. Yeah.
So if
So
not, yeah, let's go ahead.
yeah, thanks for the nice talk, Kwesi. So I was just actually very, very interested because, there is a very recent work by Anders Rancher from Lund University who proposed like minimax adaptive control algorithms, where he took like a dynamic game approach to almost a very, very similar problem of yours. And the question that I have in my mind, I strongly encourage you to look into that. The question that I have in my mind is like, have you thought about doing a regret analysis, meaning that you compare your learning effort against some optimal controller in hindsight which knows the dynamics exactly? So you get to know like how much the adaptive controller is paying the price for not knowing the dynamics exactly. Have you considered like doing some regret analysis? That's my question. Thank you.
Thank you for the question. Sorry, awesome. But yes, I was going to say, I encourage you to look at Ju's presentation if you're interested in things like regret analysis. So I haven't thought about this, but Ju, especially in the stochastic domain, has specifically thought about things like the regret analysis for similar adaptive controllers. But no, I have not yet.
Let's thank Kwesi once again. Hi, folks. We're back from the coffee break, and we're ready to start the second of the 3 groups of 2 talks. Our next speaker is Karen from NVIDIA. Karen, please.
Thank you, everyone, for being here. I realize the title of my talk is different from the one I submitted, but it's still about the same thing, so I apologize for that. But yeah, at the beginning in the introductions, as you all know, I'm at NVIDIA right now, but I'll be joining as an assistant professor at the University of Washington in September, which is frightening, like very scary that it's only a few months away from now. But yeah, today I'll be talking about kind of safety in the context of these dynamic, uncertain, and interactive settings. And I'm going to use autonomous driving as a prime example as I go through my talk. But a lot of things I'm going to talk about can be extended to other applications. Okay, so first I'm going to just quickly revisit the typical prediction, planning, and control stack pipeline, which is something that Eric had mentioned earlier today. And so we have this prediction model that will predict how other cars or other agents around the robot's going to behave. And then the predictions will be then fed into a planning module that will decide what is the best trajectory to take, considering the interactions and reactions from the surrounding agents. And then this optimal trajectory will be then fed into a low-level controller that will try and track the trajectory as best as possible. Okay, and so the 2 questions that I'm really interested in, and I'm going to talk about it today, they are 1, where does safety come in? Again, I only have a couple of slides on this because this is based on some prior work. But if you look at the stack, there's actually a bit of diffusion of responsibility that's happening. A common argument is that if your prediction model is really good, that's very accurate, then that means your planner is going to be safe because there's a good idea of what the other agents are doing. And then your controller will just blindly follow whatever the planner is going to do. But obviously, for these kind of deep learning based prediction models that, again, Eric mentioned in his talk, your prediction model won't be 100% correct. It's going to make a mistake, or it won't capture tail events very well. And then this must mean that your planner is going to be misinformed, and then it's going to kind of make a mistake or give a unsafe plan. And then your controller is just going to blindly follow this. So the question here is, where does safety come in? So yeah, I'll only have a couple of slides on this. The second question, which will be the focus of today, is what does it mean to be unsafe? I know that, we all talk about we want safe control, we want safe systems, but if you take a step back a bit, it's like, if given a situation, like how do you tell that your robot is safe or unsafe, right? And the kind of a challenge here is that actually different stakeholders have different interpretations of what it means to be safe. What a regulatory body thinks is safe is different to what a control theorist thinks is safe, and it's different from what a passenger thinks is safe. So what does it mean to be safe or unsafe? Okay. So as I said, I'm just only going to have a couple of slides on the first question. So I'll jump back to that. So this is based on some prior work I did a few years ago. And in this work, I looked at how we can incorporate a safety monitor or safety filter, and how we can construct minimally interventional backup strategies for your robot that is operating in these interactive scenarios. So the example I have here is a traffic weaving scenario where you have 2 cars that are initially side by side and must swap lanes in a short amount of time. And I'm sure many of you have been in a similar situation when you're trying to merge onto the highway and there's another car trying to merge off the highway at the same time. And there's this kind of somewhat even challenging, even for humans, a challenging negotiation that, that we have to go through. And so in this work, we used a neural network to predict the future trajectory of other agents. And then this is then fed into a probabilistic planner. And this is based on prior work. And so, yeah, basically this, this planner takes in this neural network prediction model. And this is what I will refer to as an interaction planner. And then, as I mentioned before, like
the planner will feed an optimal trajectory to a low-level tracking controller. And this tracking controller is going to track this trajectory as best as can, subject to some higher fidelity dynamics model that the planner would typically use. And then while this is all happening, kind of in the back, we're going to have a safety filter or some kind of safety monitor that is kind of monitoring how safe is your system. And the technique I used in this work is based in Hamilton-Jacobi reachability, which I'll talk more about in the next few slides. But the safety monitor is, in the background, is just running. And then whenever, it believes that your system is unsafe, what I do in this work is I pass a safe control constraint to the low-level tracking controller. And this is in contrast to what like a common method, a different method, and perhaps a more common method is to actually override the low-level tracking controller. But, what I do is by passing a safe control constraint to the low-level tracking controller, the low-level tracking controller is still minimizing for tracking error. So it's still trying to do what the planner wants to do, but now it's willing to just minimally deviate from the planned trajectory to the extent necessary to stay safe. And we found that this kind of gave a better balance between safety and efficiency. And so on this slide, I have some kind of videos, and this is in these videos, this is in simulation. And so in this first video, you have the robot car or the autonomous car in red, and then the human-driven car, which is actually me on an Xbox controller controlling this human. And I'm going to like kind of carelessly swerve into the robot. And this safety monitor, which is rooted in Hamilton-Jacobi reachability, you can think of this as some buffer zone or some safe set around the robot. And it will say the system is unsafe whenever the human kind of enters this zone. And you can see that the size and shape of the zone will change according to the states of your system. Okay, but in this first video, this is when there is no safety monitor being applied. And you will see that it kind of sucks. So it kind of goes right through it. And those lines coming out of the green car are the robot's prediction of what the other car's going to do. So I mentioned before, there's a prediction model that is running there. If I play this again, you can kind of see that the robot planner like tries to slow down. So you can see that the line coming out of the red car is the planned trajectory, and it kind of turns dark red for a moment because it's trying to slow down. But this interaction planner just wasn't kind of good enough. It wasn't quick enough to respond. Now in the next video is the case where we just switch to the optimal collision avoidance controller. And as I mentioned, like by just completely overriding what the planner wants to do, you lose a lot of performance from it. So you can see in this video, kind of the same thing is happening. The red car, you can see it swerves and brakes, but it's like completely off the road, which, on the highway, there's actually road boundaries. So this is actually pretty unsafe. Even though it avoids a collision, it kind of went off the road, which isn't great. And then in this next video, this is what we are proposing, which is a minimally interventional safety controller, where it passes a safe control constraint to the tracking problem. And you can see it swerves as well, brakes, and then but very quickly gets back on track. And it doesn't go off the road as much as the previous video. And then so we also tested this on a full-scale vehicle. So on the bottom right is X1, which is a fully autonomous car that was developed by the Dynamic Design Lab at Stanford. And X1 here played the role of an autonomous car. Unfortunately, no one would give us a second full-scale car to deliberately swerve into X1. So we did the next best thing and got a 1/10 scale RC car. So it's a little hard to see in the video, but you can see it has a little LiDAR visible mast, so we can track it. And on the bottom, you can see as it kind of swerves into X1, X1 was able to kind of just swerve away just enough to avoid a collision, but very quickly get back onto the road and finish this traffic leaving maneuver. Okay, so this is all fun, and kind of the results that we saw was consistent with our hypothesis. But let's take a step back and kind of really ask ourselves, was the safety monitor that we used really the best monitor? Right? As I mentioned, we were using Hamilton-Jacobi reachability, which in the typical fashion assumes a worst case policy of the other agent. But on the real world, like we can't drive on the road thinking everyone around you is out to get you and deliberately trying to, crash into you. So can we do better, right? Can we change this assumption a little? So actually, let me ask this question, but a little differently. So given this scenario, is the autonomous car safe? Well, it depends. It depends on how you extrapolate the cars into the future when making this collision check, right? And this extrapolation process can be quite complicated and challenging, right? Because it can depend on the uncertainty in how humans behave. This extrapolation process can also depend on contextual information, right? Depending on the road geometry, for example. And there's also the question of how responsibility is allocated between agents, right? Depending on where you are on the road, maybe you are more responsible for yielding than others. Unfortunately, there's actually, we're not very close to converging to an answer right now. There's no consensus between stakeholders, so industry, researchers, and academia, and even regulators. And so to me, this is a very interesting yet challenging question. And this is what I really want to get to the bottom of. And hence, hopefully you guys have great ideas on how to solve this as well. Okay, so another thing I want to add is that safety is subjective, right? What is safe in theory doesn't necessarily mean is going to be safe in practice. There's also this notion of like perceived safety, like different passengers have different kind of risk tolerance or safety tolerances. So it's quite subjective as well. So that also adds to the challenge. Okay, so before I move on to the details, I want to first define this term safety concept. So it's not anything too technical. It's just more of a terminology I'm going to use throughout the talk to help unify some existing related theory that has been used in the past. And so when I talk about a safety concept, I'm talking about two mappings, so two functions, that is mapping from world state to one, a safety measure, and two, a set of allowable safe controls. Okay, again, like this mapping is, I'm not saying anything specific about this mapping. It can be very complicated, right? You can take in perception information, uncertainty, road geometry, all that stuff. But basically, there are kind of two outputs that it will give, right? Safety measure and allowable safe controls. And what I'm going to talk about in the next couple of slides is that Hamilton-Jacobi reachability is actually a way to synthesize a family of safety concepts. Okay, so I'm going to assume not all of you know what Hamilton-Jacobi reachability is, so I'm just going to spend one slide summarizing it. Usually it would take like a lecture or something. But basically, Hamilton-Jacobi reachability, or HJ reachability, is a kind of a method to help us answer the following question. Does there exist an ego policy to avoid a collision set, assuming that the contender or the other agent is doing the worst thing possible to cause a collision or to drive your system into the collision set? Okay, so first, we need to first define the collision set, right? So given the joint state of your system, you can say this region is when the two cars or your two agents are in collision. And you could imagine that there is a larger set that contains this collision set where no matter what your ego agent or your robot does, there is nothing there's nothing it can do to avoid a collision, right? So for example, the contender could be right behind their ego, but moving at a higher velocity, right? They're not touching each other, so they're not in the collision set, but because the contender vehicle from behind is moving at a much faster velocity, your ego is unable to accelerate or steer fast enough to avoid the collision, right? So conversely, if you were to be outside of this larger shaded region, then it is possible for your ego to avoid the collision set, okay? And this larger set is what is called the backward reachable tube, or kind of colloquially, I'll refer to it as the avoid set. And computing this avoid set boils down to solving the Hamilton-Jacobi-Isaacs partial differential equation. So if you're familiar with the Hamilton-Jacobi-Bellman equation, it's very similar. It's just kind of like the robust version of it. So if we can solve this PDE, then we have this backward reachable tube. And so the idea is that you first define a scalar valued function v of x, where the 0 sublevel set is precisely the collision set. And then you kind of plug it into this PDE, propagate this backward in time. So it's accounting for the dynamics and the optimal policies of each agent. Oops. And you know that your solution V, which is called the HJ value function, kind of will change at each time. And then the 0 sublevel set of your solution is precisely the backward reachable tube. Okay. Okay, if you didn't follow all that kind of the math, the details here, that's okay. Really, the takeaway I want to get at here is that HJ reachability is a way to synthesize a safety concept, because the solution V for that PDE is precisely a measure of safety. And if we can compute the set of controls that prevent your value function from decreasing, then that is also precisely the set of allowable safe controls. Okay. Now let's take a closer look at the HJI PDE. So, so that was the same equation I had in the previous screen, but I want to kind of point out some of the tuning knobs that this PDE has that we can kind of play around with. So the first tuning knob we have is here's my mouse, is the control sets of each agent. So U is the control set of your ego, and D here is the control set of your contender vehicle. So typically, kind of in the most vanilla setup, these control sets are set to be the set of dynamically feasible controls of each agent. So you can think of this as maximum steering, like left or right, or the maximum acceleration or deceleration an agent can take. But, you know, like there's no reason why we can choose something different. And kind of going back to what I mentioned earlier on is like, it's not that, like, is it reasonable to assume the other cars on the road are deliberately trying to crash into you and they're going to maximally steer and maximally accelerate into you? Probably not, right? Otherwise, if you do assume that, you're going to result in very conservative behaviors by the ego. And so, for example, so instead we could maybe consider the fact that maybe the contender vehicle is likely to brake in this situation, or your ego can only accelerate in the situation, right? I mean, we can choose whatever we want, basically. So maybe to kind of make this idea more concrete, consider a lane following situation, which is a lot of highway driving. And you have the contender vehicle at the front, right? Does it make sense to assume that the contender will aggressively decelerate? I mean, they could, but the thing is, that's actually illegal, right? Brake checking is I think, is kind of illegal. And if a collision were to happen, it might not actually be the ego's fault, because your front car should not have been slamming on the brakes unless there was a really good reason to. And so there's kind of this notion of like, who was at fault? It kind of enters this equation, which I don't really want to get into because that's also very challenging. And so the question then is, what are reasonable acceleration limits for the contender? I mean, we can still, we should still assume that they can brake, but maybe not brake maximally. Maybe they brake 50% at 50% capacity or something. Okay, and so another tuning knob we have in the HJI equation is kind of the types of policy that each agent is following. So if you see here, we're assuming a max-min formulation, because this is assuming the ego is maximizing this value function. So it's doing everything to avoid the collision set, whereas oh no, I lost my mouse again. Okay, and the contender is minning. So it's doing the worst thing possible to cause a collision. But again, there's no reason why we can't change this around, right? So we can consider maybe a max-max formulation, a min-min formulation, or a min-max formulation. Like, I mean, you have to have good reason why you're choosing this, but the point is you could change your assumptions on the types of policies that each agent is following. And so kind of given these tuning knobs of this HJI equation, we can, like, this is why we can kind of describe and represent and synthesize a family of safety concepts. And we can describe safety concepts that depend on open loop non-reactive policies and also closed loop reactive policies. And so not only can we, given given that we've, tuned those knobs and synthesize, so not only can we come up with new safety concepts, we can also recover a lot of existing safety concepts that are prevalent in existing literature. I think the interesting thing here is that, there's all these other concepts, but they don't actually mention HA reachability anywhere in the formulation. So I think one of the contributions of this work is that we are unifying a lot of existing kind of seemingly disparate concepts under the same framework. And so maybe you've heard of like forward reachability, reach avoid games, worst case dynamic games, which is like the vanilla HA reachability formulation. From industry, from NVIDIA specifically, there's the safety force field. From Intel Mobileye, there's the responsibility sensitive safety. Maybe you've also heard of velocity obstacles. You can also view contingency planning as an instantiation of a reachability problem. And there's many more, many more that I might not have covered. And so I think it's really exciting that we can kind of describe and unify a lot of existing safety concepts, because that means we can compare and contrast different concepts. We can, depending on the autonomy stack you're building, you could swap out, you can test out different safety concepts really easily, because now they are all represented in the same way. So I think that's pretty cool. So a lot of this stuff you can actually find in a preprint that we have online. So I encourage you to check this out. This is like a blue sky paper, so it's actually only, depending on what format you use, it's only 4 pages. So it's a very quick read, but it will give you a quick overview of what HA reachability is, how we can recover kind of those safety concepts that I had on the previous slide, and kind of what we think are really important and challenging and impactful research questions to look into. And so I'll end my last slide here with kind of, what I think are important research questions. So the first question, and this is something I kind of briefly talked about in the middle of my talk, was how do we restrict these control sets? So I mentioned before, we could restrict it however we want. We can, choose what it choose this, there were the pink and blue boxes that I had on the axes on the bottom right before, but we got to be reasonable when we're choosing these control sets. So, so the question is can we learn these control sets from data, right? Because we want to make sure that, whatever safety concept that we're using is going to be reflective of how people drive in the real world. So learning this control restriction from data, I think, is an interesting direction. And then the second question is, well, suppose we found this way to restrict the control set, how do we actually incorporate it into the safety concept synthesis? How do we actually incorporate it into HA reachability formulation? Depending on how this restriction takes place, it can make the reachability problem significantly harder. The third question here is, how can we leverage behavior prediction models? Again, there's been a growing body of work in developing very kind of complex behavior prediction models. And so maybe we can leverage some of those developments in order to predict how people would behave in safety critical situations, and then use that for our safety concept synthesis. And then the next 2 questions. So what is the definition of responsibility and how do we model it? So something I mentioned at the very beginning was this kind of, different agents on the road have different levels of responsibility. First, I don't really know what responsibility means. I think it's relative as well. But what is a formal mathematical definition of responsibility? I don't think currently exists. If you do know, please come talk to me in the break afterwards. I would be very curious. But coming up with some formal definition of responsibility, I think, is challenging. And then incorporating that into your autonomy stack is also another challenge. And then the other question is, how do we account for varied context? So safety, I do not believe, is static. It changes depending on the road geometry. It depends on the location, like geographic location as well. Even the time of day can kind of change what safety means. Like how people drive during rush hour traffic is very different than how they drive, at midday or something. And then the last bullet point here is addressing the curse of dimensionality. So this Hamilton-Jacobi reachability computation that I talked about suffers from the curse of dimensionality. So this means that the types of system we can work with is extremely limited. Otherwise, if we go anything bigger than like 6 or 7 dimensions, the computation essentially becomes intractable unless you have some like supercomputer. But that does not mean that we should ignore, discount HJ reachability, right? I still think it's a useful inductive bias in how we can think about safety concepts and begin to synthesize it. The actual details of the computation, I think is an interesting research direction. Like we can lean into maybe techniques from reinforcement learning, which is all about estimating or approximating this value function, which is exactly what this HJ value function is. We can look into ways to implicitly represent the value functions like neural networks. The challenge there is that, if we're talking about safety, we also want something that is kind of interpretable and easy to verify. So if we start using neural networks, then it can make the safety argument very challenging, especially when you're presenting this to regulatory bodies, because they kind of need some certificate to say, like they like to see some formal certificate, especially when it comes to safety. Oh yeah, and then I guess I have a preprint coming soon. I'm still working on it, but I think hopefully I can put this online soon, a paper online soon, which addresses the first 2 questions. And so with that, thank you for your time, and I'm happy to answer any questions.
Thank you, Karen. Questions for Karen?
Yeah.
First of all, great talk. And I have a question. When you presented the different examples, like the quantum simulation with the autonomous car and the human car, how do you define the unsafe set that it is around the autonomous car machine?
Yeah, so for that, I used Hamilton-Jacobi reachability. So I did the same computation. So maybe I can go to the equation. So the way I did that was I had to formulate the relative dynamics between the 2 cars. So I was working with the relative state and the relative dynamics, and then I could just plug that in and then solve it. To kind of add a layer of conservatism, I used a higher fidelity model for the ego vehicle and a lower fidelity model for the contender vehicle. So by doing that, I'm assuming the contender vehicle is more agile than it really is, whereas the ego car is less agile because I'm using a more accurate model. At the same time, because this resulted in a larger state dimension, I was somewhat sacrificing on the kind of grid size in the computation. So obviously you can solve this PDE explicitly, by like discretizing your state and, solving it. So the quality of your solution also depends on how dense your grid is when you're solving this. So I had to make some sacrifices there, but hopefully that answers your question. Yeah.
Some people break out. So I'm wondering if it is easy to incorporate models in the hybrid
Yeah, that's a really good question. So currently, as it stands, of what I'm showing on the screen here, that doesn't really account for uncertainty. You could have, so the kind of the standard formulation where I use D there. So D typically stands for disturbance. But if you're talking about a relative system, the disturbance is the other car. But you could add additional disturbance terms in your dynamics to say, okay, there's a bit of noise or process uncertainty in your dynamics, and you could be robust against that. You could, I think there's some work on like risk sensitive reachability, but I think that work is very like, I'm not too familiar with the details of that work, but if you're going to look at stochastic settings, this will turn into a stochastic PDE, which I've heard is very challenging. So there could be that. I think also, if you have uncertainty in your estimation of the other agent, you can still compute the reachability as normal, but then you just have some ellipsoid, and you would maybe evaluate the mean value of that ellipsoid or something. But yeah.
Thank you.
Yeah, you had a question?
Nice work, very, very relevant too. I think in a way, this is the way we all try to drive, is doing these reachability analysis in our head, right? As you drive down the road, we have to have a tremendous amount of trust in the other drivers. When you're hurtling down, I-75 at 80 miles an hour. And there's another aspect there, which is that I think we're trying to judge the other drivers' safety, capability. If you see somebody weaving or you see somebody driving erratically, you automatically want to back off and give them more space, expand. So, so is there any aspect? I mean, maybe in future work is to use your learning on the other cars and try to assess their safety. So that can affect the criteria for adjusting your reachability.
Yeah, that's a really good question. So, maybe if I go to this slide, so you could maybe one way to kind of address the question that you asked, which was like, can we use some online estimation of how the other agents are behaving to dynamically adapt our safe zones or our reachable sets? So you could do that. So one way is we could augment your state dynamics with an additional parameter, which is describing maybe the upper and lower bounds of these control sets. So it's like a parameterized reachability computation. And then online, you could, predict how the other agent's behaving and then somehow learn, okay, what are the control limits that this agent is likely to follow, and then do a lookup for that particular parameter value. So you could do that, but this will add to your state dimension a whole lot. So that will make it intractable. And that, I think this is like, your question, I think, is related to my my third question here is like, how can we leverage these behavior prediction models to make our reachability compute or restriction of these control sets more informed? So yeah, I think what you said is a good question. I don't have concrete answers right now.
And in real time, assessing the other drivers, their level of safety. I mean, there's a great old story about the preacher and the drunk driver.
Okay.
And the other thing is have you extended? Can you extend this to multiple vehicles?
So yes, yeah, so multi-agent, I think is a good question. Unfortunately, for the reachability computation, it would just not be tractable because you can't solve it as you extend to multiple agents. I think you can get pretty far by looking at pairwise interactions and just looking at each possible pair of agents. I think practically you only really interact with like at most 4 agents around you or something, right? You don't need to consider all the agents, everywhere, because that's not how we drive. And maybe you're not even responsible for collision avoidance for, a car that's 3 lanes across or something. So I don't have a good answer right now on how we account for multi-agent scenarios, except that you can get pretty far with just looking at pairwise interactions.
We have one question
Okay.
in chat. Can you read that question? Or I can read it.
I can read it out. The value function is a function of time. Question: how far in time was this strategy considered for the computation? Are we talking about seconds or minutes for collisions to occur, or does it matter? So that's also a good question. So as part of the reachability computation, you have to propagate it backwards in time over some horizon. So this horizon can just depend on like whatever you choose this horizon to be, but maybe like 2-3 seconds, or depending on how much look ahead you would like your system to have. Depending on your system as well, your value function can converge. And so you can look at maybe the infinite time horizon kind of system, but I mean, you just have to solve the solution for a long time and just check if it converges. But I think for the experiments I had, I think it was like 5 seconds. So we're talking about orders of seconds. But yeah, the designer is free to choose.
Cool. Thank you, Karen. Let's thank you so much again.
Thank you so much.
So our next speaker is Lillian Ratliff, who unfortunately couldn't join us and will be joining us over Zoom. So let me try to figure out how to make that happen. Okay, so let's first sound up. Oh, this is still sharing. Okay.
How can I stop sharing? Oh, there we go.
This doesn't sound like it's gonna be good if I unscrew it. I'm torturing you. Thank you. Usually what the students tell me. Lily was sharing. Okay.
Nope, that's not what I want.
I think you can just leave it be and then.
Should I share now? or-
Yes, please. Oh, this actually sounds pretty good. Okay, perfect. Let me just put this on.
So can you hear hear me and see my screen?
Yes, we can. Let me see if I can get this.
I hear like a feedback.
You should change the view thing. No, the other one, the view button. Standard one.
Perfect. That yes. So let me mute us then.
You can start, Lily.
Okay, it's hard. I don't hear anything, so it's hard for me to know if I can start or not. So I guess because it's on mute, I don't know. So I'm going to assume that I can just start talking. Okay. Yeah, so I'm going to talk a little bit about some of the work that we have going on related to learning from decision-dependent data. And I'll get into sort of what that means throughout the talk, but I just want to comment on the sort of connection to the workshop, which is focused, largely on safety critical systems and learning in safety critical systems. So the concerns I'll talk about are sort of safety adjacent. So specifically, I'll talk about issues related to bias and strategic behavior that can impact the learning process. And so these things, of course, may ultimately lead to safety concerns in critical systems. Okay, so to sort of motivate things, I want to sort of start with the traditional view of learning, where we typically think about training our algorithm using some past data. So we'll train our algorithm and then we deploy it in the world. And our decisions take actions. And we don't really take into consideration that those decisions may impact the underlying data distribution, meaning that the past data we trained on isn't necessarily relevant anymore. And so in particular, this is true in a lot of different infrastructure systems or large-scale intelligence systems where we have humans embedded in the loop. And so to start, I'll give two motivating examples of some issues that can occur. So the first is related to distributional shift and bias. So our algorithm, and so here I'm thinking about, training supervised algorithms or using supervised learning. The algorithm itself may change the underlying data distribution. And a good example of this is feedback reinforced bias in predictive policing. So this is results of a study cited at the bottom of the slide here. And so basically what you see on the left-hand side is two plots of the Bay Area. So in the top, you see drug arrests from 2010 and where those are concentrated in red. And on the bottom, you see estimated drug use from a national survey in 2011. You can see how that's distributed, and it's not at all the same as the drug arrest. And then in the center, you see the result of Predpol's algorithm for predicting hotspots. So telling police where they should go and patrol to look for illicit activity. And you can see those are more consistent with the past drug arrest data as opposed to the actual estimated drug use. So what's happening is that we're seeing feedback reinforced bias in the data and institutional bias. So on the right, you can kind of see the result of police targeting for illicit drug activity by race. And you can see that's also not consistent with estimated drug use by race. And so that was 2016, and there was some data leaked from the PredPol server at the end of 2021 showing this problem is still persists and is arguably more widespread. So on the right, you can kind of see where places that are using PredPol and in red, and then the black dots are using other predictive policing algorithms which have similar concerns. Okay, so the second motivating example is related to strategic data sources. And so this is kind of going to be the primary focus of the talk. And the issue is that you might have human users that have their own preferences and they're sort of reacting to these decision rules that are getting deployed. And so an example of this is Uber and Lyft drivers. I think this was either 2018 or 2019. There was a whole thing, a large news cycle around this where they were reported to be colluding together in something called Surge Club to trigger surge prices artificially. So what they do is they go to places like airports and congregate in these waiting areas and then all get together at once and turn their phones off. So then that triggers artificially a surge, and then they turn on their phones and capitalize on that increase in price. And so this ends up getting this extra cost gets offloaded onto the passenger side of the market, which leads to negative externalities. So you have this unaccounted for strategic behavior leading to negative externalities. And so what we want to do is think about how we can go from this open loop perspective of, say, training a algorithm from data that we assume is static, as you see on the left at the bottom, and move towards a closed loop perspective where we now take into consideration our data distribution depends on the decision of our algorithm. And we're sort of a control community, and so we go, okay, we do this all the time. And so sort of the subtle difference here is that the way that this data distribution depends on our action is unknown a priori because it's potentially generated by these strategic users who have their own private preferences, which are not easily solicited from them. And so there's this game basically between the decision maker and the sort of decision dependent distribution, leading to sort of information asymmetries because of the lack of knowledge of how that data distribution depends on the action. This is what sort of makes this problem difficult. And so as an example, we can think about, and I'll use this as a running example. So we can think about this rideshare platform, and what they want to do, let's say, is they want to predict demand as a function of their surge mechanism in various features. I'm just showing supply here as an example. So once they've trained their algorithm, they then use it for various things. One thing they may use it for is creating these heat maps that they show to the drivers. And the drivers can then use these to be strategic in how they plan their day to maximize their individual revenue, or they can use this information to behave in adversarial behavior like we saw with the collusion. And so then what ends up happening is now your supply should be modeled more as a function of the surge mechanism because of this strategic reaction. And so in the work we've been doing lately in this area, we've have some results on the adversarial and strategic user setting, as well as two other settings which are interesting, in particular to us folks in the control community. So the first is where you have additional dynamics. So what can happen is that users take, in a lot of behavioral models for human users, they often compare to reference points or some history, or even some exogenous input like information from their friends, et cetera. And so you can capture this sort of history-dependent behavior through some set of dynamics. So we have some results designing algorithms for that setting. And the second setting is adding in competition. So of course, in the rideshare platforms, drivers and passengers both typically do price shopping, and they use both platforms. And so across all of these settings that we've been looking at, one of the sort of main insights is that we've been able to leverage game theoretic abstractions, in particular to capture this information asymmetry between the decision-dependent learner and the data distribution to be able to address some of these challenges. So we don't have much time, so I'm just going to focus on one of these areas in particular where you have competition between multiple decision-making entities. So of course, this occurs in not just rideshare markets, but also in mapping apps where you have a variety of different platforms that are giving routing suggestions to users who then execute them in the same environment. This also occurs in other applications like university admissions or loan procurement, where there's multiple institutions that have different desiderata for their classification criteria, whether you get a loan or whether you get into university, and applicants try to meet those different criteria. Okay, so I want to start with first, why is the base problem of decision-dependent learning hard? And then we'll talk about layering on these additional complexities. So if we just look at this single player decision-dependent learning problem, where we now have in our optimization problem, the data distribution depends on X, we can write down first order optimality conditions, which are shown here at the bottom of the screen. And you can see that there's two components. The first one is the derivative with respect to the explicit dependence of the loss on the action X. And that's easily computed stochastically with samples, so that's no problem. But the second component is what I'll call an implicit partial gradient. And that's not computable unless you have a priori knowledge of this data distribution. So even just optimizing this single player decision dependent learning problem is challenging. And this problem has its roots in stochastic programming and control. However, they're not thinking by and large in that literature, which exists going back to early 80s at least. They're not thinking about strategic mechanisms that are generating this data. In the modern machine learning optimization literature, however, folks have been thinking about strategic prediction and strategic classification in this context and exploiting the underlying structure of the problem to be able to design algorithms that provably converge. So what we're going to talk about today is adding this extra layer of complexity where we have competition, both in terms of explicit dependence of the loss on a competitor's decision rule, so this X minus I, as well as implicit competition through the decision-dependent data distribution. So let me come back to our little running example. So now in our demand prediction problem, the supply not only depends on, say, Uber's surge mechanism, but also Lyft's. And so what I'll do in the next few slides is talk about two settings. And the goal for both of these is to define an equilibrium concept and then some algorithms. And then what I'll do is just conclude with some interesting open questions. Okay, so in the first setting, we're going to consider naive learners, where they basically just ignore this implicit partial gradient. And then we'll see what happens there. So that's sort of what people already do in practice, which is why it's important to study. Then we'll look at the non-myopic setting, where players actually try to form some gradient estimate of that full gradient, including the second term. Okay, so we'll start with the naive case. So if you look at the single player case, what people do in this naive setting is they do something called repeated retraining. So they deploy a model XT. They, run their, they deploy a model XT. They run it for some time, looking at the performance. They look for model drift. Once they detect this based on some heuristic, typically, then they'll retrain, which means they'll sample from that distribution generated by XT and then re-optimize. In the multiplayer case, we can extend this very naturally. So we do the same thing. Each player deploys their model XIT. That impacts the collective joint action, impacts each player's individual distribution. They wait till they see retraining, and then when they update, they play a best response, given that the other players are also playing a best response. So in the single player case, you can easily see the relevant sort of equilibrium concept is just a fixed point of this map. So that's what people call a performably stable point. And to extend this to the multiplayer case, what we do is we define an auxiliary game. So we're going to define this game G that's induced by this joint action profile Y. You can see Y shows up in this data distribution. And then the game is just in terms of the explicit dependence of this loss on all the players' model parameters. And so then naturally, this update just becomes a Nash of the game induced by xt, so the previous xt. So this leads naturally to this performably stable equilibrium. And I put equilibrium in the title on quotes on purpose because it's an equilibrium of this dynamical process and not necessarily of any game. So each xt plus 1 is a Nash equilibrium of some game, but it's not ultimately going to be a Nash equilibrium of the original game. So we have to be careful about that distinction. All right, so what we want to do now is come up with some algorithms that will converge, and we need some assumptions. So we're going to assume that we have convex compact strategy spaces. So this ensures we're going to have some existence. And then we're going to ensure or assume that for any joint action profile Y, the game induced by Y is alpha strongly monotone. And so I've put the definition for a general game for strongly monotone down here. But essentially what you do is you take the individual gradients of each of the, if you have a game F1 to Fn, you take the mapping that is composed of the individual gradients for each of the players. And that mapping should be strongly monotone, meaning it satisfies this inequality. And so to get some intuition for what this means, that the game induced by Y is strongly monotone, we can think about a common case, which is where there is no explicit dependence of Li on X minus I, meaning they have a separable, the game is separable in some sense. What this assumption reduces to is just that in the separable case is that the losses are going to be alpha strongly convex in the Xi's. Okay, so then we need some regularity assumptions. So sufficiently smooth cost, we need gradient Lipschitz condition, and then we also need the distributions that are induced by different joint action profiles to have some growth condition, which we define in terms of this Wasserstein 1 distance. With these regularity parameters and our strong monotonicity parameter, we define this quantity rho, which you can see at the bottom left. This is super important because it's going to determine when we have equilibrium. And so the first result we have is like just trying to understand when repeated retraining converges. And so we can show that it will converge to this performably stable equilibrium point using a simple fixed point argument, which is why we need this rho parameter to be less than 1, and why it's important, because we get sort of a contraction with rho less than 1. So this is the important regime for this class of problems, because outside this regime, we won't even have these equilibrium at all. There's no guarantee that they will exist. Yeah, I'll just skip that last thing. So that's a stylistic algorithm. It's just saying, if you have the ability to compute these Nash equilibria at each iteration, then this is what it will converge to. In practice, what people will do is something more empirical. So in particular, they will do what's called a repeated stochastic gradient play. So what this means is that players sample data from the distribution induced by the previous action, and then they follow a part of their individual gradient, which they can compute. So this is important here that this is not the full gradient. So dropping the I index for simplicity, you can see that this term in the update is just going to be a stochastic version of this explicit partial gradient, but it ignores the second component there. So we can show that this process also converges to performably stable equilibrium if we have appropriate variance bounds, and the rate at which it converges is what you expect. So we have to be in the regime where we have existence, so rho less than 1, and then you get a rate that matches what you would expect for a stochastic gradient method. So there's the variance bound on the top, and then we have the target accuracy epsilon in the numerator. And to improve this, you can do batching, etc. Okay, so that is this sort of traditional setting. So what people tend to do in practice, because they don't have access to this data distribution. So it's important to understand that. But what we want to do is kind of move to a setting where players are no longer naive, and they can actually take into consideration some information about how other players, or how that data distribution is changing. So again, those performably stable equilibrium are not a game theoretically meaningful equilibrium in the sense that players have an incentive to deviate. So in particular, there's some component of their gradient that they could potentially follow to improve their cost locally. And if we then take into consideration that decision dependence in the data, we get a well-defined game theoretically meaningful concept, which is this Nash equilibrium. So the goal again is going to be to come up with algorithms that obtain game theoretically meaningful points. And I'm skipping sort of the results that we have on existence. So we just basically show when, given the structure of this problem, and specifically the structure of that second component of the gradient, we give sufficient conditions under which the game will be strongly monotone. And if it's strongly monotone, we know we get existence. So let's suppose we're in that regime. So then now we want to come up with algorithms that actually converge. And so we look at two. The first is the setting where we have no knowledge of this implicit partial gradient. We still want to form a gradient estimate. So we do something called a derivative-free method. And I'll give results for that. And to improve the sample complexity, we move to a setting where we have a parametric description, and we take tools from adaptive control and design an adaptive, what we call adaptive gradient play. And so players essentially form an estimate of this full gradient by estimating the parameters of their decision-dependent distribution. So I'm going to give the results for the bandit feedback or derivative-free setting for general strongly monotone games, because we actually improved the known rate for that general class of games. And the decision-dependent learning problem that I formulated, that decision multiplayer performance rate prediction problem, is an instantiation of a strongly monotone game under the sufficient assumptions on that second component of the gradient. So the results we have are as follows. So if we consider a strongly monotone game on our convex compact joint action space, we can define a smooth loss function. So that's basically this F delta here, where the smoothing that we're doing is that we're drawing this some W from uniformly at random from this set U, and then perturbing with query radius delta each of the actions according to in the direction corresponding to each of the components of that vector W. And then taking the expected value with respect to that. So that's the smoothing mechanism we're looking at. And so how that gets instantiated in terms of the algorithm is as follows. Each player is going to form a gradient estimate using a single query of their loss function. So each player's gradient estimate G hat I is going to be formed by them perturbing their individual action, sampling VI from the unit sphere with an appropriate dimension. And then the oracle is going to give them back an evaluation of their loss function, taking other players' perturbations. Then they're going to form this gradient estimate, and it's known that this is an unbiased estimate of the smooth loss function. So then once we know that, we can just basically relate the smooth game to the original game in order to get some convergence results. So once they have their gradient estimates, they then do a projection, following that gradient. And what's important here is they're projecting onto a retracted, they're taking their constraint set and retracting it in a way such that they're never querying outside that constraint set. So for example, this might be important in safety critical applications where you don't want to violate some safety constraint that's on your problem. So you shrink the radius of that set to ensure that doesn't happen. And so prior known convergence rates for this setting were given by Bravo et al. In 2018. And they showed that the rate was epsilon -3 in terms of target accuracy. But conjecture it should be epsilon -2 because we know that the lower bound for single player case is epsilon -2. So we were able to get that rate. And I'll just kind of give some intuition for how we do it quickly, because it's this sort of interesting or cute little argument. So essentially what we do is that we define 3 different games. We define the original game on the original set. So then we have a Nash equilibrium for that game. Then we define the game in terms of the smooth losses on the retracted set and the corresponding Nash equilibrium, which is X delta. And then the original cost on the retracted set. And that gives us a Nash equilibrium X bar. And then we can take our iterates and break them up. And the second 2 terms we just bound using a structural stability kind of argument as follows. So the first term, it's on the same constraint set. So we can just use the fact that F delta is the smooth perturbation of the F from the original game. And then for the second one, the cost functions are the same, but the constraint set is now different. So we can just use some relationship between the normal cone of these sets in order to bound the second term. And both of these terms are bounded in terms of something like delta times some quantity, some instance-dependent parameters for the problem. And then the first term, we can then just use standard convergence arguments because we know we're following the gradient of an unbiased estimate of the gradient of the smooth losses. All right, so that gives us a improved rate for derivative-free methods on strongly monotone games, which these decision-dependent learning problems are under reasonable regularity assumptions. However, those rates can still be prohibitive, and so we want to do something a little smarter if we have some knowledge, some prior knowledge of the data distribution and how it depends on our action. So I'll just quickly go through this. So basically what we do is that we look at an important class of distributions for this performative prediction problem, which are called location scale distributions. And so you have a location and scale parameter, and then we look at the parametric case where our location parameter depends on our actions in the way that's shown here. So linearly in terms of our own actions and the actions of competitors. And then we just do basically what you would do in adaptive control. We inject noise, sufficient noise to be able to ensure that our online least squares estimate of these parameters is converging appropriately, and then update using an estimated gradient. So that's basically what's going on here. We inject our noise, we run an estimation scheme, just online least squares, and then we project or we update using a projected gradient descent for each player, where we now have an estimated estimated implicit partial gradient component in addition to the explicit partial gradient. So I won't go into the details, but with appropriate step size choices, we can show that this adaptive gradient play will converge with the rate you expect for any stochastic gradient method. I mean, you can kind of see this in this little toy example on the right or on the left. The key idea here, which I think exposes some interesting questions for this problem space, is that we're leveraging these ideas from adaptive control, that if you can inject sufficient noise, you can ensure your estimation problem is persistently exciting. And so what's potentially interesting here is that we can leverage techniques from adaptive control and other online learning settings where we know certain classes of functions are persistently exciting, such as radial basis functions and the like, and try to get more, be able to give these kinds of algorithms for more complex data distributions. Okay, so I have a couple minutes according to my clock. So I'll just quickly go through the last couple slides. So I want to show one quick simulation, and then I'll just have one slide of like future work comments. So let's consider this Uber Lyft example that I've been talking about throughout. And so let's suppose that Uber and Lyft want to individually maximize their revenue with some regularization term here. And they have this linear demand, which you can see here, which has this sort of performative effects, just like in the adaptive algorithm setting that I was just showing, where these different coefficients are price elasticities essentially. So we can take some data from this Kaggle Boston data set that has both Uber and Lyft prices together or rides together. And we can construct what's called a semi-synthetic example where we can simulate basically these performative effects on top of doing sampling from the data set. So we bin all of our data into $5 bins. We have different empirical distributions for those different $5 bins. And then the decision here is going to be the surge price. So how much of a delta beyond the price. So the X here is going to be this, the surge pricing mechanism for each of these bins. So I'll skip the first example. So the one I want to show is this comparing the performatively stable points to the Nash equilibria and their performance and what this means in terms of social welfare. So there's some interesting phenomena here. So I'm showing two different price bins. On the left, you're seeing the price of anarchy. So this is a comparison between the social cost at the equilibrium concept, Nash or performatively stable point, relative to the social cost at the social optimum. So we want this to be closer to 1 in the case of this setup. And you can see that these are in the $10 price bin, these are pretty comparable, the performably stable and Nash. While in the $15 price bin, there's some difference between the two. But what's interesting is if you look in the $10 price bin, even though the Nash equilibrium and performably stable point have similar prices of anarchy, the market share split between Lyft and Uber is significantly different. So even though it seems like it's good from a social welfare point of view, there's some potential fairness or equity issues related to how the market ends up getting split. And in particular, this would be important if you had a small company relative to a big company. These companies are arguably comparable, I guess, at this point. So there's an interesting set of open questions around understanding fairness as it arises in these decision-dependent learning problems where there's competition, and how that impacts the ultimate, the ultimate performance basically of these different companies. Okay, so I'll just sort of wrap up with this last thing. So I talked a little bit about what we've been doing in terms of modeling competition in these decision-dependent learning problems. And we looked at the fairly basic setting where you have abstracted out sort of the strategic behavior of the users in terms of this data distribution. So there's interesting questions in terms of incorporating additional constraints that are economically motivated, such as individual rationality, or being more explicit about incentive compatibility in terms of these strategic users. So trying to understand what their actual utilities are and how that impacts the data distribution. There's interesting directions to think about in terms of looking at behavioral psychology models, for example, where we are actually incorporating issues related to risk assessment. So, this may not be important, for example, for choosing, which rides to take in a rideshare platform, but it may be important if you're trying to use these kinds of models, for instance, in a more safety critical context, like autonomous driving or something of that nature. There's also interesting questions. So the last thing I'll just point out is there's interesting questions, and this kind of relates to the last example that I gave, related to looking at when you have not just multiple firms, decision-making entities, but also multiple populations of users, where some of those populations may represent different socioeconomic groups within society. So you may have like lower income, middle income, higher income, and let's say you have a bunch of banks that are giving out loans. You don't want the end market share split in the setting to be such that a institution with a lower credit rating ends up serving the lower tier socioeconomic group. We want to ensure that there's some sort of fairness in the way that the market splits. And so we have a recent paper looking at this, which we just put on archive on Monday, which has some interesting results showing how markets actually split when you have these multiple populations with differing preferences and types. Okay, with that, I'll just sort of end. If there's any questions, I'm happy to answer them.
Thank you, Lillian. I don't know if we have time for questions. Were there any questions on Zoom maybe? Okay, so in that case, let me suggest that we thank Lillian, and of course we can talk to her offline, and then take a short break for, let's say, 5 to 10 minutes, and then start with Kevin's presentation at 4:50. Thank you, Lillian, once again. Okay. Hi, everyone. Thanks for sticking around. We're starting the last of our trilogy for today, the last two talks, and our first speaker is Kevin from Burrell.
Good afternoon, everyone. So I'm Kevin McDonough. I work at Burrell Applied Research. We're a small aerospace research company located in Hampton, Virginia, which is, Norfolk, Virginia Beach area. And we do a number of different things, from wind tunnel testing to aerodynamic modeling to working on UAM path planning. And so that's going to be the focus of this talk. And it's really going to talk about some technologies that we've developed through some. All right. So this talk's going to cover some technology that we've developed as part of SBIRs and STTRs for the Navy and the Air Force. SBIRs and STTRs are small business research grants that the government gives out. And while they're not a perfect indication of what the government or different agencies and regulators are interested in, it does give some insight into what concerns they might have relating to different areas, different problems, and gives you an idea of what they might be thinking. And so just to note, the STTRs, I worked with Professor Ella Atkins from the University of Michigan and Professor Ornik from Illinois on those projects. And the goal of this talk is, as I said, to provide insight into different information sources that can be used to enhance the safety of urban air mobility, UAM, and advanced air mobility operations. Urban air mobility is a real big thing right now, where people are trying to figure out how to really integrate these unmanned systems into urban airspaces. How can we have sky taxis? How can we have drone-based package delivery, things of that nature. And so for the purpose of this talk, I'm going to discuss two types of risk, and I call them planned risk and reactive risk. So planned risk is risk that you assume when you are actually planning the operation. So I'm going to fly this path. How risky is that path? What could happen while flying on this path? Reactive risk is how do I react to unknown a priori risk? So collision avoidance, or maybe there's something that changes the airspace that you need to adapt to, things of that nature. But really the question is, what information exists so that you can actually assess these risks and plan accordingly for them? So as I said, we have planned risk and we have reactive risk. And so planned risk, we can have risk to populations. Is anyone actively in danger if we do this mission? Risk to infrastructure, are we going to run into the local substation and take out power for the city? Operational risk, how critical is the success of this operation? Does this need to happen for whatever reasons? Are you trying to deliver that heart from one hospital to another so that person doesn't die? Hopefully, you can complete that one. Or system degradation. So you can plan for what happens if my UAS platform malfunctions? How can I adapt to those malfunctions? And then you have reactive risk, and these are the traffic avoidance, conflict avoidance, public safety emergencies that might crop up. So if there's a building fire and that's right in your path, should you change your path to avoid that building fire? And then, natural disasters and inclement weather. This can impact where it might be safe to fly and how risky your operation really is going to be. So I'm going to focus on risk to populations, risk to infrastructure, and then touch on conflict avoidance and public safety emergencies. So unconventional versus conventional information. There's a lot of information out there and a lot of different sensors that unmanned systems can use to try to assess what's going on in the world around them. For aerospace and for drones, you've got your ADS-B, you have radar, LiDAR, other ranging sensors. And what's becoming a lot more common is visual and infrared imaging, computer vision type sensors. But for some unconventional information, this could include audio broadcasts. So air traffic control is really useful in trying to figure out where aircraft might be. Drones don't always use that because they don't necessarily have the processing to take advantage of that. Now, if there is a manned operator somewhere sitting in a room, they could be listening to you to ATC and participating with ATC, and then that's a little bit of a different problem. But for an autonomous unmanned system, that is a different question. And then we also look at using land use and population information, and this helps us assess the risk to people, to infrastructure, and try to plan accordingly. So both the conventional and unconventional sources of information are rich in content, and they can provide different bits of information that can complete the situational awareness problem for UAS operations. So planned risk is the acceptable risk assumed at the beginning of a UAM operation. And I apologize, I'm going to probably use UAM and AAM interchangeably. And if someone is really upset about that, I apologize. It's not an intentional thing. So to estimate planned risk with respect to populations and infrastructure, we want to look at the aircraft reliability and where that aircraft might impact in the event of a failure. By impact, I mean, crash. The chance, and we also want to estimate the chance that that aircraft is going to strike people or critical infrastructure. And so we want some sort of metric, a risk metric that can scale with population and altitude, can scale with mission parameters. It accounts for different platform sizes and configurations, and it can also account for a variety of additional risks and different weights. And so in one of the STTRs we did, we came up with this formulation of the risk, this metric. And it just separates risk to populations, risk to infrastructure, and then risk other. And that's a generic catch-all for anything else that someone might want to add later. But it's, like I said, it's designed to be generic and it's designed to encompass a whole bunch of different factors. But specifically, risk, RP and RI, these are the terms that are there for the striking of people and striking of infrastructure. So how do we want to try to actually calculate the chance of striking a person or some sort of critical infrastructure within the path of the UAS? And this is a very conservative estimate where your drone is flying and it just stops working and falls out of the sky in some sort of ballistic trajectory. You can do a whole lot of different things with this, and you can have more intelligent predictions. This one is made to be fairly conservative for the purpose of this talk. And so the chance of impacting an object at XYZ, we have the area of the estimated object, or the estimated area of the object. We have the estimated reliability of the UAS platform. We have the glide ratio of the UAS, and we have the area of impact, which is just the glide ratio times the altitude. And then rho I, that is a population of an object within whatever grid cell you're searching over, or the area of the impact. So how can we estimate this? And this is where we bring in the land use information and the population information. And so there's a lot of different databases out there for different urban areas Some of them are open source, some of them are not. And they can give you knowledge of where you have different critical infrastructure. And this includes power generation and distribution, hospitals, parks, stadiums, educational and religious centers, things of that nature. These systems are often called GIS, geospatial information systems. OpenStreetMaps is a good open source one that gets better every year because people are adding more and more to it. But then you also have some municipal data sets that are available. SanGIS for San Diego is actually really great, and they update it. I forget the last time they updated it, but it's a fairly regular process. And so depending on the areas, you might have really good knowledge of this, or you might have pretty poor knowledge of this. It depends on if the data exists. Now, as far as populations go, this is where it gets a little bit trickier. Ideally, if we knew where everyone was at every point in time, we could do this estimation really well. There are obviously some issues with privacy and figuring that one out. So we can't necessarily have that information right available to us. But we can make estimations of where people are going to be given time of day, day of week, based on the land use. We also know population distributions that are documented from national censuses. And so that varies from country to country, but the US decennial census, it is pretty good at the beginning of the decade and obviously diminishes in quality at the end of the decade. But you can use Landscan out of Oak Ridge National Laboratory, and that provides a nice usable, ingestible data set to figure out where people might be just based off of the population. And as I said, dynamic sources like anonymized call record or location service information, those are really hard to get. So if any of you work for Verizon or something and want to partner up on that, please let me know. But we've tried to get some of that information in the past, and it's not very easy, and understandably so. You don't necessarily want to be able to track a single individual. So this is an example that we did for population and infrastructure-based path planning. So we want to plan a path that is low risk to people and critical infrastructure. And our test case was San Diego, California. And the scenario, it's a little trivial, but bear with me. We're marine researchers who want to use a drone to take a sample from a research vessel out in the ocean to San Diego State University. And so what is a path and operational time that provides low risk? And so what we did was we took the population density of San Diego, and this is from Landscan, and we also used land use from SanGIS. And this provides us two risk images, is what we called them, that we can filter and put together in a way that we can actually assess what we imagine a total risk might be for this operation. Why do we call them images? Well, if we, in the way that we defined the actual risk altitude-based, you can create a convolutional filter on this where you can, based off of your altitude, just filter it differently to get a different risk assessment for that altitude. And so it's very much within the computer vision image processing sort of realm right there. And so we developed these risk images, we put them together, we have this total risk image, and we go through different iterations of figuring out when it might be suitable to fly this mission. And we find, 11 p.m. on a weeknight is low risk, and that makes sense. Anyone here really familiar with San Diego? So this is only looking at stuff on the ground. And it also flies pretty close to San Diego Airport. And so there's obviously some issues with that. So this would just be one piece of that puzzle where, this path is low risk for one area, but we're going to need to, think about it three-dimensionally. And so, again, this is just one piece to a total picture. but it's an important piece. And I bring that up because there's a lot of research right now on trying to figure out how best to plan UAM routes in different urban areas. How should we consider that? Should we consider it along commuter lanes? Should we consider it along what populations exist where? Should we consider it on what reduces travel time to key areas? And there's different research out there and people are trying to figure out what this answer is, but not a lot of people, at least that I've seen, are considering how risky is it to run these operations to people underneath these lanes. You're talking about putting more and more traffic in these lanes, and every time you increase the population of the aircraft, you're increasing the risk that something could go wrong. And so if something goes wrong, where is that thing going to land? Is it going to, hit a school or a bus full of nuns or whatever, PR disaster you can imagine? And so the argument, I guess, that I'm trying to put here is we need to consider that as well as what's in the air. And by making these lanes, it's effectively deconflicting the traffic already, because these lanes are going to be UAM only, and we'll see what happens. But this is an active area of research where both researchers are coming up with ideas and regulators are pushing back with, I don't know if that's going to work. And so this will be, I'm sure, an active area of discussion in the coming years. Now, as I was saying, we need to consider the airspaces themselves as well when we're trying to plan this stuff. So airspaces in urban areas are also often very close to terminal areas, terminal being airports, because airports are often located in urban areas. That just kind of makes sense. Now, airspace maps, like we see here for the San Diego region, that tells us where aircraft might be. It gives us typical aircraft lanes, it gives us transit routes, but it doesn't do anything about the active aircraft and where they're currently being scheduled. Sensor output like ADS-B and radar can provide insight into where aircraft currently are, but not all aircraft use ADS-B. Those are typically called non-cooperative aircraft, and it can be difficult to figure out where they might be if you only have ADS-B. And radar, depending on how big of a system you need or want, that can be pretty expensive. And then we have ATC communications, and this is intended for manned aircraft, but it provides insight into where aircraft likely will be in the future, because not only are you getting the information of where an aircraft currently is, but you're getting information on where it's being routed. You have to decode that information from ATC speak into real physical world, but if you have that capability, then you can probably come up with good estimations. So if you have the capability of listening in on the broadcasts, and this was another SBIR that we did, you can take the ATC communication and you can run it through natural language processing and speech recognition to identify what is being said. So maybe they're saying climb and maintain to 10,000 feet. And then you want to extract data from that. So what is actually being told to that aircraft? It's saying whatever your current altitude is, increase to 10,000 feet. And so you might not know exactly where they are right now, but you know that pretty soon they're going to be at 10,000 feet. You might want to avoid 10,000 feet. Or you know that they're going to be climbing through the airspace that you're currently participating in. So autonomous unmanned operations require intelligent signal processing to interpret the ATC and pilot communications. And fortunately, ATC communications belong to a pretty strict and structured subset of English. And to my knowledge, English is the language that's used for all ATC communication in the world. So that's even nice too. It's just one language. And while the structure can be non-standard, and it does appear encoded if you are not a pilot. I'm not a pilot, but I had to learn how to, encode or decode it. It's suitable for autonomy through machine learning and AI. And this provides autonomous systems with insight as to where traffic might be. And the nice thing about ATC communications is it includes all traffic participating in the airspace. Whereas ADS-B transponders are only going to be the cooperative traffic. And it will require knowledge of or a searchable database of arrival and departure procedures, navigational aids, and all of this stuff. But fortunately, the FAA and ICAO or ICAO, the International Civil Aviation Organization, they publish these databases and they're updated, I think, every 27 days. They're not generally updated in a dramatic way, but they are regularly updated. And similarly to ATC communications, emergency messages and public safety messages are broadcast in the clear as well. And so you can do a similar process on identifying where there might be a building fire or where there might be some sort of operation where you want to avoid that. Because maybe there might be police helicopters flying in that area or something of that nature. And so, again, you use the same process where you have speech recognition, you extract the data, and then you add that in your set and you can update your path accordingly. So realistically, UAM operations and AAM operations are never going to be risk-free, no matter how good we make everything. But there are several different information sources available to reduce the risk of these operations. Urban environments are dynamic and complete situational awareness is also not possible. But conventional and unconventional aerospace information sources exist that can really reduce the risk of these operations. Many of these technologies that I've been going over, they can be folded into what's known as a UTM, an unmanned traffic management system. And I suspect that certainly as you get UTM systems up and running to really try to manage some of this traffic, they're going to have these capabilities because it's almost necessary for them too. And then, you know, I didn't touch on platform reliability or resilience at all in this talk. And so if you don't have a reliable platform, then it doesn't really matter what information you're using. It's probably not going to be good enough. And so that is something that obviously has to be considered. And the UAM and AAM manufacturers, they're doing a pretty good job these days of testing and validating their systems. Most of that comes from some of the insane amounts of money that are now being put into UAM, I think because everyone wants flying taxis. But there's a lot of information out there. And this information can be used in a lot of different ways. And it's just a question of how can we tap into that? Intelligent systems are allowing us to tap into different sources of information that otherwise have not been used in aerospace and also in self-driving cars, in all sorts of different autonomous applications. And so the question is, how can we use all of this information? And so while I talked about UAM operations and AAM operations because that's what I do, I want you all to, you know, leave here thinking, what information can help me really solve my problem? And is that information able to actually be used in some interesting way? Because most of the time the information exists, it's just a question of where is it? And so if anyone has any questions, I'd be happy to answer them. If anyone has any answers, that would be really great too. But with that, thank you all for listening.
Our last speaker is Changliu Liu, who is also joining us over Zoom because she unfortunately couldn't be here. So let me see if we can set this up. Okay, I think we are ready. Changliu, please start whenever you want.
Cool, great, thank you. And can you hear me?
All good, yes.
Okay, great. Thank you so much for organizing this workshop, and it's really unfortunate that I cannot join in person. Today, my talk is going to be on how can we ensure safe human-robot collaboration. And I will talk about how to do the safe control and how to learn high fidelity human models in order to make sure that the collaboration is carried out safely and efficiently. So a little bit about motivation. And by the way, please feel free to interrupt during the talk. I'm very happy to take questions on the way, and I'm also monitoring the chat. Okay, so robots are actually entering our daily lives, and they all have different modes of interactions between robots and humans. My research is mainly focused on transportation and manufacturing. So in manufacturing world, we have those collaborative industrial robots, which will collaborate with human workers on a variety of assembly tasks. And then on the transportation side, we have autonomous vehicles and also autonomous drones that will interact with other road participants. To ensure these kind of interactions happen in a desired way, we first need to make sure these interactions are safe. So let's first look at what are the kind of safety problem or the safety specification we want to enforce. And then I'll talk about some challenges to enforce those safety specifications when we are in a human-robot system. And then I'll talk about approaches that we develop to solve those challenges. So the safety problem here we're considering is a kind of hard constraint problem. So we require the state of the system to be confined in a safe set. It's a set on the state space shown as the blue here. So the first property we want the system to have is the forward invariance property. That is, if we start initially from the safe set, the system will never leave the safe set. And then the second property we want a system to have is the finite time convergence. That is, if we start outside the safe set, we should go back to the safe set in finite amount of time. So back to the human robot system, how does this safe set look like? So here is one example of human robot collaboration where we have a human worker and a industrial robot arm, and they are doing some joint assembly task. And then from this scenario, we first abstract out a computation model where we use capsules to wrap up all the geometries of the robot link and also geometries on the human body. And then from there, we can define the safe set as the set of human states and the robot states such that and the distance between any points on the robot capsule to any points on the human capsule is greater than some threshold. Yeah, and then the constraint on the robot state and human state gives us the safe set. So since the human state and the robot state is of high dimensional, it's very difficult to visualize how does the safe set look like. So I'm projecting it back to a 2D space where the horizontal axis is the robot state, the vertical axis is the human state. And this constraint is essentially a non-convex constraint, which is represented as this blue area. And suppose we're already on the edge of the safe set, then the robot should first predict what the human will do. And then based on the prediction of the human behavior, in this case, it's going up, the robot should act accordingly to ensure that the system still stays safe. And to automate this process, we can introduce a scalar function on top of the state joint human robot state space. And we call this function as the safety index. The safety index is defined such that the system safe set is a sublevel set of this scalar function. And in literature, this can also be called as control barrier function or a Lyapunov function. And with this safety index, then we can easily determine how should the robot move, because any control that drives the system state above the sublevel set is unsafe, and any control drives it downward is safe. And this criteria can be checked just by looking at the time derivative of the safety index. And if our system, the human robot system, is control affine, x dot equal to fx plus gxu, then the phi dot can be computed as this linear function on the robot control u. And then the constraint enforced on the time derivative of the safety index can be translated to a constraint enforced on the control. And this will be a half space constraint on the robot control space. And whenever we have this constraint, then we can just project the nominal robot control towards the set of safe control that is defined, that is calculated from confining this time derivative of the safety index. And then we can add this safety notion as a supervisory loop to any nominal controller. And in this way, we can guarantee the forward invariance and the final time convergence. Yeah, so this is very good approach to address safety. And this works very well if we have very good model of the system. So for example, we have demonstrated this idea on this industrial robot arm. This is a Fanuc robot arm. And as we can see, the robot arm has some planned trajectory as shown in the yellow curve here. And the robot does not always follow the planned trajectory because it needs to avoid this moving obstacle in real time. And the supervisory loop, the safe control in the supervisory loop is helping the robot to modify the trajectory. Cool. So this is the general idea, but there are a lot of challenges to scale this method up to solve the real world, to ensure safety in the real world human-robot interactions. Because when humans are in the loop, we do not explicitly know the system dynamics. It's very difficult to predict the human behavior. So in this way, then how can we perform safe control without explicit control-affine dynamic model is a challenge. And I'm going to talk about some black box optimization methods that we developed recently to overcome this challenge. And also the second challenge is how can we get a high fidelity model such that our safe control is not overly conservative. And then this is the second topic that I'm going to talk about is how to identify the system dynamics using verification guided learning. Okay, and in the following talk, we assume that our system dynamics is some neural network model. It can be any other parametric model, but it's just complicated to be interpreted by our humans. So we need advanced methods in order to make sure that we can still apply safe control. Okay, so before we work out the math for safe control using neural network models, let's first consider the fundamental problems to synthesize safe control. Essentially, there are two fundamental problems to synthesize a safe control. The first is we need to synthesize a safety index such that for any state in the state space, we should always have a feasible safe control when our control space is limited. Yeah, and then the second question is, how should we compute whenever we have a valid safety index? How should we compute the safe control in real time? So for the first question, it's actually an offline synthesis problem, and for the second question is an online synthesis problem. And this figure is to illustrate the idea. The safety index is a function on top of the state space, and for any state, we have a constraint on how the safety index should change. So for example, for this X1 state, it's unsafe, so the safety index should drive the system towards the safe set. And for the state X3 is on the boundary of the safe set, so then we should not leave the safe set, and the blue areas are valid safe control direction. And but this is only on the kind of state space and on the time derivative of the safety index. With the system dynamics, we transfer this constraint back towards the control space. And previously, if we have a affine dynamics, this transformation is a linear transformation, and we still have a half space constraint, so which is easy to deal with. And previously, we didn't consider any control limit. Now, if we don't have a control affine dynamics and don't have an explicit dynamics, it's very difficult to characterize the valid control. And also it's very difficult to check whether the valid control has any intersection with our control limit. That is, if there's any intersection between the blue area and the yellow area. And with that, we need to introduce some black box optimization in order for us to ensure that we can always have a valid safe control that is an non-empty intersection between the blue area and the yellow area for all the states. Once we get that, we should be able to compute the real-time safe control. Yeah, so to answer the question that I raised, we'll first answer question 2. That is, how can we compute the online safe control? Because this is a little bit easier to explain. Whenever we have a valid safety index, which guarantees we can have find a valid safe control, then we can solve this optimization problem that maps the reference control to the set of safe control defined by the safety index. The only challenge is that this constraint is not a regular constraint. It can have very rough edges. But the advantage for this formulation is that the objective is still a convex objective. So then the optimal solution should always lie on the boundary of this constraint. And with that, we can just do multiple direction line search. And whenever we touch the boundary of the set of safe control, we just record that solution, and then we find the optimal solution among all the directions. Yeah, so this can address the second real-time synthesis problem without an explicit model. And the first question, that is, how can we do the offline synthesis without an explicit model? With that, we can just use data-driven method, and we can just write a good loss function for us to synthesize a safety index such that the intersection between the safe control and the valid control, the blue and the yellow area, is always non-empty. And with that, we can write out the optimization problem as the following minimax, actually max min. Inside the min, we find inside the inner optimization is to find the state such that the intersection between the blue and the yellow area is the smallest. And then we need to find the safety index parameters such that the smallest intersection is being maximized. Yeah, and we develop a solution strategy to solve this max min problem efficiently by first parameterize the safety index using some prior knowledge, and then solve this minimax iteratively. Okay, let's look at one example. This is a simplified example since we are not explicitly dealing with the human robot system. We are just dealing with a vehicle model that is interacting with a static obstacle, but the challenge is that we do not explicitly know the vehicle model. We just have a black box vehicle model which we can query the output. But we do know that the vehicle model is second order. And our safety requirement is that the vehicle should not bump into the obstacle. And we write it as this distance between the vehicle and the obstacle should always be greater than or equal to the minimum threshold. Yeah, and using our prior work, we find that there's a class of feasible, viable safety index that can be parameterized in the following way, which is adding a constant C and then add the power to this threshold, the minimum and the distance, and then add some constant and minus some constant multiplying the relative velocity between the vehicle and the obstacle. And in our previous work, it is shown that if we parameterize the safety index in this way, then we can ensure forward invariance inside the original user-defined safe set. Yeah, and with this parameterization, then we can start to optimize the parameters in the safety index, that is the constant C, the power N, and the this coefficient K, in order to ensure our previous objective is being met. And here we show the optimization process using this. This is the face portrait. This is phi 0. That is whether the distance is smaller than the is greater than this distance threshold, and the vertical axis is the relative velocity between the vehicle and the obstacle. So without synthesizing the safety index, the original safety requirement defines this green area, but this green area cannot be made forward invariant because if we check the control space for each state x1, x2, x3, x4, for x2, there is no valid control that can keep the system inside the safe set. If we optimize one step, we can find another safety index. And the resulting four invariance is this green one. And for all the states that we had previously, we can ensure that if it's inside the safe set, it will not get out of the green area. And if it's not inside the green area, the system will convert, the state will converge to the green area, as shown here. And if we optimize further, we can get maximized feasible safe control, as shown here. So the main difference between this index and the last index is lie on the state X3. For the second one, the valid safe control for X3 is has a very pretty small area, but for the last one, the valid safe control for state 3 is pretty big. And then we can use this to control our system to ensure safety. And this method does not depend on any configuration of the system. Whenever it is synthesized, it can generalize to arbitrary obstacle configuration. Cool. And also we have applied this method as a safety monitor to a deep learning agent. Even though we do not explicitly know our system dynamics here. This is the this evaluation environment is the safety gym environment, where we have a second order vehicle that need to learn how to go to the goal without hitting the obstacle here. Although we do not explicitly know the dynamics of the vehicle, but we can still do the synthesis and safeguard our learning agent, which is using a PPO, reinforcement learning algorithm. And we can guarantee 0 training time violation and also finite time convergence. Okay, so this is how we do the safe control when we don't explicitly have the system dynamic model, where then we do the black box optimization. And the second problem is, how can we get those black box models at the first place? Here we consider the human model. So usually we can just collect a bunch of human model and then do the model learning. Then we get some prediction model, which can be used to synthesize the control. And when we are synthesizing the real-time control, we get the real-time state measurement of the human. Then using the human model, we can generate the prediction. So the pipeline works, but the key challenge is that the distribution of the human data may shift between online measurement and offline data. And in order to deal with that challenge, we need to do some continual learning in order to make sure that we can capture the real-time distribution of the human data. And for the continual learning, there is also two versions. One is to do just online adaptation. Whenever we get new data, we just update our prediction model, which I will skip for the sake of time. And I'm going to focus on the offline version. That is, before we see the real-time data, we should generate some adversarial text to our current model and ask human subject to label that data in order to make sure that we have sufficient data coverage in order to make sure that our model is robust enough. The motivation for that kind of adversarial data augmentation is that usually to generate human model, we will not be able to get a bunch of free data. To collect human data is very time consuming, and also human may work on different tasks, different environments, and interact in different ways with the robot. So it's very challenging to get a full coverage of the human behavior. But essentially, we do not need to have a full coverage of human behavior in order to learn the robust model. The most informative data we should have is those most confusing data to our current model. What does that mean? That means the data on the current decision boundary is the most critical for us to make sure we have correctly learned. So for example, if we have a 2D classification task, here as shown in the ground truth is shown here, we get a bunch of data. The data distribution is not perfect. And then as a result, the learned model is shown here. Although it has learned several clusters, but the decision boundary of the cluster learned is not perfectly matching the ground truth. And then to make sure our model is kind of robust, the most informative new data to add to our data set is those boundary data, as shown in this white points, and we can query the experts to label those boundary data. And whenever we get this correct boundary data labeled, then we can do the training and improve the performance of our model, as shown in this animation here. Yeah, as we add in more and more, our estimation will be gradually converging to the ground truths. So this is the key idea of this continually learning new data using a text to our current model. And we developed this framework to instantiate this simple idea, where we have some initial data sets and some augmented data sets. We use all the data for the training, and whenever we get the trained network, we do network verification to find those boundary data. And whenever we get the boundary data, we will see whether we need to ask the human to verify the label for that data or not. And once we get a verification, we will add this data directly to a larger pool surrounding the original training set. And if we do not have a valid label, we just add it to the adversarial data set. And with this, we compare this method with other training approach, for example, the conventional supervised training and the conventional adversarial training. As we can see, our method can gradually improve the performance of the prediction accuracy of our human model, so which is the desired outcome. Yeah, and just for reference, this approach can be applied to any kind of data. It can be just trajectory data, which is encoded by low dimensional skeleton motion of the human, or can directly apply to the image input. So here we are doing intention classification for the human subject when it's interacting with the robot. And the first row is the data we collect, and second row is the perturbed image using that approach. Although you may see the perturbed image is very similar to the first row, but if we do the differentiation, we can still see the difference. And in this way, we do not need to adjust the lighting condition, adjust the environment to get a bunch of human data. We just need to use the approach that we have to synthetically generate the input. And if the generated input or image does not have the same label, we can ask a human to verify that. So in this way, we will not include false information in our learning system. Yeah, and for the attack method, we use our toolbox neuroverification.jl, which implement a variety of sounds and formal algorithms to kind of compute some optimization over neural networks. Cool. With that, I would like to conclude my talk. So in today's talk, I focus on the 2 challenges to achieve safe control for human robot systems. I started with the safe control for human robot system if we have known control affine dynamics. Then I talk about how can we relax this control affine dynamic assumption and use black box optimization to deal with unknown, deal with the inexplicit dynamic model. And then we talk about how can we use verification guided learning to obtain robust human model in order to make sure that the human robot system is not overly conservative. There are some ongoing work for this framework. So for example, our safe control currently is only kind of being a supervisory loop that is monitoring the nominal control. Then it's possible that the safe control is limiting the exploration of our nominal control, which will result in some bad local optima. Then how can we balance the kind of safety and exploration? It is explored in our paper that is going to be presented in the ACC conference in the following days. And the second topic we're exploring is that can we simultaneously learn the policy and the safety certificate if we do not have the system model? This is also reported in a paper that is going to be presented in L4DC pretty soon. And in some cases, we might have some physics-based human model regarding like human muscle movement, but a lot of times the human intention is still hard to predict. So can we then in this way merge those model-based approaches and model-free approaches to get high-fidelity dynamic learnings? I think the answer is yes, we have done this exploration for kind of driving behavior prediction, and we're currently trying to do that for human skeletal motion prediction. Yeah, and for the continual learning, I barely touched only the verification guided learning version, where we use some feedback through human subjects to make sure that we can continually learn from new data. But there can also be feed-forward adaptation, that is to prevent catastrophic forgetting when we are adapting our model. Cool. So with that, I would like to thank you for your attention and happy to take any question from here.
Thank you, Changliu, for the talk. Any questions for Changliu? I don't know how we're going to organize the questions. If there's any questions, raise your hand and start shouting. Please.
Okay, I'm gonna shout. So in your
By the way, Changliu, can you hear Karen speak? Maybe Karen, if you want to come up here.
Hello. Okay, so my question is, when you were learning the safety index function, you had that kind of structure. I guess, like, where does that come from, and is there like an interpretation for that particular function form? Thank you.
Yeah, that's a great question. Let me go back to, so this is totally based on the understanding of the physics. So first, we know that our system is second order. So then if we have a first order safety index, that means the safety index, the lead derivative from, sorry, the relative degree from the safety index to the robot control is degree 2. In this case, we cannot use the control to immediately affect the safety index in certain cases. For example, in this example here, if our system is on the boundary of the original safe set, that is, the distance is on the threshold, and the system has some relative relative velocity towards the obstacle, then no matter how hard we apply the acceleration of the vehicle, the collision is inevitable. So in this way, we need to add higher order terms to the safety index. And how many higher order terms we add depends on the order of the vehicle dynamics. In this way, vehicle dynamics is second order, then we only need to add the relative velocity here. And in terms of the powers here, this is actually a very interesting observation that we made in my the ACC 2014 paper. That is, we can freely modify the original. So as I said, we first need to add higher order terms. The higher order term can be directly added to phi 0. And after that, we can freely modify how phi 0 is represented, as long as the modified version has the same sublevel set as the original phi 0. So for example, if we add d to d main to the n power minus dn, the sublevel 0 sublevel set of this function has the same sublevel set of the original d mean minus d. And we have proved that with this, we can still have forward invariance if the power and the coefficient for the higher order terms are correctly selected. And the interpretation of doing this kind of shaping is that we can actually use the power to generate some nonlinear boundary of the final forward invariant set, as shown here. Yeah, so because we had some like a power here, we do not necessarily need to have a linear boundary for the final forward invariant set. Yeah, I'm not sure, does that make sense?
Thank you. Thank you. Karen is saying it's good. Okay, I guess that's it. Any last minute questions? If not, we are slightly above the promised time. So I just want to thank everyone again. Thank thank all our speakers. Thank, of course, everyone who participated in the workshop. I hope you found it educational. I hope you found it fun. I hope you found it to be a good start of ACC. Most of our presenters, most of the speakers, the organizers, we will be here for at least parts of the conference. So I'm sure that we would all love to talk to you further about our work about safe control. We are planning to hopefully post these talks, permitting good quality of the Zoom recording, to YouTube. We will see how that goes. We'll keep you posted on that. And of course, feel free to talk to the speakers if you want to get their papers or slides or whatever it is. Thank you once again for coming. This was really an honor to have you all here.